Have you ever stopped to think how something can be in two places at once, or how two particles can stay linked even when separated by light years? Tonight, we're exploring the quiet strangeness beneath reality, the world that makes everything possible. Welcome to The Sleepy Scientist. This channel is all about calm curiosity, where you can learn something new about the universe without rushing through it. I'd love to know where you're watching from and what time it is where you are. It's always fascinating to see how far these quiet journeys reach. If you enjoy peaceful explorations of science, please give the video a like and consider subscribing. It really helps. And to those already subscribed, thank you. You're the reason this little corner of calm keeps growing. Don't forget to tap the notification bell so you won't miss the next slow drift through science and space. Hopefully this video isn't too interesting to keep you awake, but if it is, at least you'll fall asleep knowing a little more about the most mysterious part of physics. Because once you look closely enough, the universe starts behaving in ways that no one can fully explain. Quantum physics began with a problem that refused to go away. Light sometimes acted like a smooth wave, yet other times behaved like tiny particles. Matter, thought to be solid and predictable, turned out to shimmer with probability. The deeper scientists looked, the more the old rules of nature fell apart. Out of that confusion came a new idea, that everything is built on uncertainty. Energy doesn't flow continuously. It arrives in steps called quanta. Particles don't follow single paths. They explore every route until something makes them decide. An empty space isn't empty at all. It hums with invisible energy, flickering constantly in and out of existence. Tonight, we'll explore these quiet truths one small piece at a time, 101 moments where logic bends and nature shows its subtle mathematics. You'll hear about superpositions that let something be two things at once, entanglement that connects particles across light years, and the strange vacuum that hums even in silence. Each fact is like a window into a smaller world, where order is uncertain and uncertainty itself becomes order. So let's begin with the smallest steps of all, the ones that built the modern universe quietly from the inside out. The word quantum comes from the Latin for how much. It describes something counted, not continuous, a world made of steps instead of slopes. In the early 1900s, scientists believed that energy flowed smoothly, like water pouring from a jug. But something strange began to happen in experiments with light and heat. Energy refused to behave continuously. It arrived in small, exact amounts, as if nature were paying in coins instead of banknotes. This was the birth of quantum physics, the discovery that reality itself seems to count. The idea first appeared through the work of a German physicist named Max Planck in the year 1900. He was trying to explain the light given off by hot objects, like iron glowing in a forge. Classical physics predicted the wrong colours, an impossible, infinite brightness in the blue part of the spectrum. Planck's solution was radical. He suggested that energy could only be emitted or absorbed in specific packets, which he called quanta. Each packet's size depended on the light's frequency and a new constant of nature, now known as Planck's constant. This tiny number, roughly 6.6 times 10 to the negative 34 joule-seconds, defines the grain of the universe. It's unimaginably small, yet it sets the rhythm for everything that happens at the atomic scale. At that level, the world begins to blur. Particles are no longer tiny billiard balls bouncing predictably along neat paths. Instead, they behave like waves of possibility, spread out over space, overlapping and interfering like ripples on water. When you imagine an electron inside an atom, it's not whirling in a perfect orbit like a miniature planet. It exists as a cloud of probability, a fuzzy region where it's likely to be found. The boundary between particle and wave becomes more like a mood than a rule. This was a staggering shift. For centuries, scientists had sought certainty, precise laws, definite locations, and predictable outcomes. Quantum physics replaced that comfort with probability. It doesn't tell you exactly where a particle will land, only the odds of finding it in each possible place. That might sound like a step backward, but it's actually a more powerful way of describing nature. Where classical physics fails at the extremes, inside atoms, near the speed of light or at subatomic distances, quantum physics shines with uncanny accuracy. Even the concept of an event changes meaning at these scales. A photon doesn't travel like a marble rolling across a table. It travels like a story being told many ways at once. Every possible route from point A to point B contributes to the final outcome, each path adding a tiny wave that can reinforce or cancel the others. The result is a delicate interference pattern, a record of all the possibilities that could have happened but didn't. This is why the quantum world feels both ghostly and precise at the same time. Planck's constant sets the stage for this behavior. It's the measure of how grainy reality is, the smallest tick on nature's clock. If it was zero, everything would behave classically. Energy would flow smoothly, motion would be continuous, and certainty would reign. But because it's not zero, the universe hums with discreteness. Energy levels in atoms come in steps, not slopes. Electrons jump between them, rather than sliding gradually. This jumpiness is what produces the sharp colours in neon lights and the precise lines in atomic spectra, the fingerprints of elements. Without Planck's constant, there would be no chemistry as we know it, no solid matter, no structure at all. When quantum theory first emerged, many physicists resisted it. The idea that energy and matter could exist in such discrete, probabilistic ways seemed almost mystical. But experiment after experiment confirmed it. Light behaved as both a wave and a stream of particles. Electrons interfered with themselves as if they were spread out, yet struck detectors one at a time. The mathematics of quantum mechanics, developed by minds like Schrödinger, Heisenberg and Dirac, proved not only successful but indispensable. It predicted the behavior of atoms, explained the periodic table, and laid the foundation for technologies that shape our modern world. It's easy to think of probability as a sign of ignorance, as if the universe knows the answer and we simply don't. But quantum probability is deeper than that. It's built into the nature of things. Reality doesn't choose an outcome until it must, and even then it seems to choose randomly, according to mathematical rules that never miss. This randomness isn't chaotic. It's statistical harmony, the kind that makes lasers coherent, transistors function, and the stars themselves shine. Planck could not have known how far his simple formula would reach. What began as an attempt to fix a colour problem in glowing metal became the foundation for all of modern physics. His constant is now woven into equations describing everything from semiconductors to black holes. It marks the border between the classical and the quantum, between the smooth and the stepped, between the predictable and the strange. At the tiniest scales, nothing is perfectly still. Even in absolute darkness and cold, energy flickers. Empty space is alive with uncertainty. Particles appear and vanish. Fields vibrate faintly, and everything is built from these subtle oscillations. It's a world that can't be seen directly, yet it's the scaffolding on which everything else stands. Quantum theory, for all its weirdness, remains our most successful description of nature. Every test, every measurement, every prediction has confirmed its accuracy to an astonishing degree, often to better than 1 part in a billion. Airplanes fly, phones work, and MRI scanners produce images, all thanks to the same tiny constant that Max Planck introduced more than a century ago. At its heart, quantum physics tells us something profound. The universe isn't a fixed machine grinding forward in perfect order. It's a set of probabilities, waiting to unfold. Energy comes in steps, outcomes arrive by chance, and certainty is a luxury that only exists at human scale. Beneath the everyday world lies a quiet sea of numbers and waves, an ocean where every event begins as a question, not an answer. The quantum world reminds us that even the smallest things matter. A constant so small it seems meaningless ends up governing everything. The colour of stars, the chemistry of life, the rhythm of the cosmos. From these tiny beginnings, the structure of the universe emerges, not as a solid block of certainty, but as a shimmering pattern of possibilities. Light has always been a shapeshifter. Sometimes it behaves like a gentle wave, spreading out and interfering with itself, curling around obstacles and bending through glass. At other times, it arrives in sudden sparks, tiny bursts of energy called photons, each one delivering a single precise punch of light. For centuries, scientists argued over which version was real. Was light a continuous vibration or a shower of particles? The answer, as quantum physics revealed, is beautifully inconvenient. It's both and neither, depending on how you look. The story begins long before quantum theory existed. In the 17th century, Isaac Newton believed light was made of tiny particles he called corpuscles. Around the same time, Christian Huygens imagined light as a wave spreading through space. Both were partly right and partly wrong. 200 years later, experiments by Thomas Young settled the argument, at least temporarily, in favour of waves. When light passed through 2 thin slits, it created a pattern of bright and dark bands on a screen, proof of interference. Each wave from one slit combined with a wave from the other, adding and cancelling in rhythmic order. It was elegant, undeniable, and very wave-like. But then came something stranger. In 1905, Albert Einstein explained the photoelectric effect, why shining light on metal could eject electrons from its surface. Classical wave theory predicted that brighter light, carrying more energy, should always release more electrons regardless of colour. Yet experiments showed that colour mattered. Only light above a certain frequency could knock electrons free. Einstein proposed that light's energy comes in discrete packets, each one carrying a single quantum of energy. These packets were later called photons, and they behave like particles. A dim blue light could eject electrons, while an intense red light could not, because each blue photon carried more energy than each red one. From that moment, light's dual nature became impossible to ignore. When we measure it one way, we find waves, smooth, continuous, and spread out. When we measure it another way, we find particles, countable, localized, and discrete. It's as if light waits to decide what it wants to be until someone checks. The double-slit experiment illustrates this duality better than anything else in science. If light passes through 2 slits, and we do not observe which slit it goes through, we get a pattern of interference, a signature of waves overlapping. But if we set up detectors to watch which slit each photon travels through, the pattern disappears. Instead of soft fringes, we get two solid bars like bullets striking a wall. The mere act of observation changes the outcome. When performed with single photons, the experiment becomes even more mysterious. Each photon seems to go through both slits at once, interfering with itself. Yet when it lands, it makes a single dot, as if it were a particle choosing one path. Over time, those dots build the same interference pattern that waves produce. One photon at a time, nature paints a picture of duality. Electrons, too, reveal this strange behavior. They are matter, not light, tiny particles that make up atoms with measurable mass and charge. Yet when scientists fire electrons through the same double slits, they create identical interference patterns. Each electron behaves like a spread-out wave, exploring multiple paths before being detected as a single point. The line between energy and matter begins to blur. Everything, it turns out, has a wavelength, even you, though yours is far too tiny to notice. This wave nature of matter was formally described by Louis de Broglie in 1924. He proposed that every particle, from electrons to baseballs, has an associated wavelength determined by its momentum. The smaller and faster the particle, the shorter its wavelength. This bold idea was confirmed only a few years later when scientists observed diffraction patterns from beams of electrons bouncing off crystals, the same way X-rays, which are light waves, scatter. Matter was officially wave-like too. So what exactly is waving? Not a physical medium like water or air, but a probability field. A mathematical wave describing the chances of finding a particle in each place. This wave doesn't carry energy the way a ripple on a pond does. It carries information about possibilities. Before a measurement, an electron exists in many locations at once, weighted by the amplitude of its wave. After measurement, one location becomes real, and the rest vanish like unchosen paths in a story. The more physicists studied this behavior, the more they realized that insisting on a single picture, either wave or particle, was missing the point. Reality at the quantum level isn't one thing or the other. It's something deeper that only appears as one or the other when observed. The mathematics of quantum mechanics holds both views without contradiction. The wave function, a complex mathematical object, describes the full spread of possibilities. When squared, it gives probabilities, the bridge between the unseen and the measurable. This duality challenges our intuition, but it's what makes quantum theory so powerful. It explains why electrons orbit atoms in stable clouds rather than collapsing into the nucleus, why lasers emit pure beams of light, and why superconductors can carry current with zero resistance. The same equations that predict the interference of photons also describe the structure of matter itself. The wave-particle duality isn't a flaw in our understanding. It's a reminder that our categories were built for larger, simpler things. We expect objects to be in one place, moving along one path, behaving predictably. The quantum world doesn't obey those expectations. It dances between them. Waves become particles, particles become waves, and the distinction is one of perspective, not nature. There's a certain beauty in that ambiguity. The universe doesn't limit itself to our definitions. It uses both whenever it needs to. When billions of photons move together, their wave nature dominates, forming smooth beams of light. When you detect them one by one, their individuality shines through. The same is true for electrons inside metals, atoms in a gas, or even large molecules cooled and isolated enough to reveal their quantum side. What we observe, then, depends entirely on how we choose to look. A photon that behaves like a particle in one experiment will behave like a wave in another, simply because the questions we ask are different. The act of measurement doesn't just record reality, it helps define it. Wave-particle duality isn't just a curiosity of physics textbooks, it's the foundation of the modern world. Every LED, every transistor, every fiber optic cable works because of our ability to harness light's dual nature. The screens we read, the lasers that scan, the sensors that detect, all rely on photons acting both like particles to deliver energy and like waves to guide it precisely. And yet, despite all that progress, the mystery remains. Light continues to be both continuous and discrete, smooth and countable, a paradox that refuses to be resolved. Perhaps it doesn't need to be. The mathematics unites both faces into one elegant framework, and nature, it seems, is perfectly content to keep the rest a secret. At its heart, wave-particle duality is a story of humility. It shows that reality is more flexible than our language, more creative than our categories, and far stranger than our instincts. What began as a contradiction became a deeper truth, that everything in the universe is both a wave of possibilities and a single, solid fact, depending on when and how we decide to look. Superposition is one of the most mind-bending ideas in all of physics. It tells us that, at the quantum level, things don't simply exist in one state or another. They can exist in many states at once. A single atom can spin clockwise and counterclockwise at the same time. A particle can take every possible path from one point to another simultaneously. Even the simple question, "Where is it?" becomes slippery, because the answer isn't one location, but a range of possibilities that all coexist until something, usually a measurement, forces the universe to decide. To understand this, imagine flipping a coin. In the classical world, it's either heads or tails. Even while spinning in the air, it's technically one or the other. We just don't know yet. But in the quantum world, before the coin lands, it's not hiding a secret answer. It's genuinely both. It's heads and tails, superimposed in a delicate combination of probabilities. Only when it's observed, when the system interacts with its surroundings, does it settle into a single outcome. This is the essence of quantum superposition, a temporary, fragile balance between all that could be and all that will be. Erwin Schrödinger famously illustrated this idea with a cat that's both alive and dead. His thought experiment wasn't meant to be taken literally. No one expects a real cat to hover between life and death. It was meant to show how absurd the rules of the quantum world can seem when scaled up to human size. Inside the box, the cat's fate depends on a quantum event, say, the decay of a single atom. Before anyone looks, the atom is both decayed and undecayed, so the cat is both alive and dead. Only when the box is opened and the system observed does the wave function collapse, selecting one outcome over the other. Schrödinger's cat isn't a creature of horror. It's a reminder of how quantum possibilities fade into classical reality when observed. This idea that reality exists in a cloud of overlapping possibilities may sound abstract, but it's the foundation of modern technology. Every quantum computer, for example, is built on superposition. A classical bit can be either 0 or 1, but a quantum bit, or qubit, can be both 0 and 1 at once, held in superposition. That allows quantum computers to process vast numbers of possibilities simultaneously, exploring a landscape of solutions in parallel. It's like trying every combination of a lock at the same time, instead of one by one. Superposition isn't just about existing in two states. It's about how those states combine. Each state carries a phase, a kind of hidden rhythm that determines how it will interfere with others. When waves overlap, their phases can add together to create bright spots, or cancel each other to create darkness. Quantum systems behave the same way. The probabilities interfere with one another, amplifying some outcomes while erasing others. This is what gives rise to interference patterns in experiments like the double-slit, where even single particles seem to know about paths they didn't take. These patterns are the fingerprints of superposition. They show that nature doesn't choose a path until it must, and even then, its choice follows the rules of interference. The bright fringes where waves align and the dark gaps where they cancel aren't random. They're precise records of how possibilities interacted before one became real. Superposition might sound mystical, but it's remarkably logical once you accept that the universe is built on waves of probability. A particle's wave function contains all its possible states, each one with a different amplitude and phase. When we measure it, we don't reveal a hidden truth, we create one, selected from that landscape according to its probability. The mathematics of superposition, developed in the 1920s by physicists like Schrödinger and Dirac, predicts outcomes so accurately that it's been confirmed in experiments to 1 part in a trillion. One of the most striking demonstrations of superposition comes from experiments with large molecules. Scientists have managed to send entire clusters of atoms, hundreds or even thousands, through double slits and still see interference patterns emerge. That means even these complex systems can exist in overlapping states, like a single object walking down 2 corridors at once. The larger the object, the harder it is to preserve its quantum behavior, because interactions with the environment tend to destroy superpositions, a process called decoherence. But the principle holds. Everything, from photons to fullerenes, has a quantum nature waiting just beneath the surface. It's tempting to think of superposition as indecision, as if particles are simply unsure of what to do. But that's not quite right. The system isn't confused, it's complete. It holds every possibility, each weighted and balanced until something disturbs it. In that sense, superposition isn't a flaw or a glitch. It's how the universe keeps its options open. Every atom, every photon, every quantum system carries within it a quiet chorus of potential realities, all humming in synchrony until the music stops and one note is chosen. Superposition also reveals that observation isn't passive. When you measure something, you don't just read its state, you help define it. This doesn't mean consciousness magically alters reality. Rather, it's the act of interaction that forces a quantum system to couple with its environment and lose coherence. Whether the observer is a scientist, a camera, or a dust particle floating in the air doesn't matter. The key is interaction, the exchange of information between system and surroundings. The moment that happens, the delicate balance of superposition collapses and the world resolves into a single story. Yet even after a century of experiments, no one fully agrees on what collapse truly means. Some interpretations of quantum mechanics suggest it's an illusion, that all possible outcomes happen, each in a separate branch of the universe. Others claim the wave function doesn't collapse at all. It merely evolves into an entangled web where every observer sees a consistent slice of reality. Whatever the interpretation, the practical results are the same. Superpositions exist and their effects can be measured, predicted, and used. Without superposition, the world would lose its shimmer. lasers wouldn't amplify light so perfectly, atoms wouldn't form stable bonds, and the colours of matter would fade into dull monotony. The reason electrons settle into their specific shells around a nucleus, rather than crashing into it, is because they exist in standing wave superpositions, patterns of probability that keep them suspended in harmony. Even the photosynthesis that powers plants depends on quantum superposition, as energy finds the most efficient path through molecular networks by exploring many routes at once. When viewed this way, superposition isn't a curiosity, it's the hidden grammar of the universe. It's what lets reality be flexible, adaptable, and surprisingly efficient. The classical world we live in, with its solid tables and predictable weather, is built on a foundation that's anything but solid. Beneath every certainty lies a sea of overlapping possibilities, constantly interacting, constantly shaping what comes next. At the quantum level, the world doesn't wait for permission to explore. It simply does. It holds every outcome in parallel until the moment it must choose, and when it finally does, that choice becomes the reality we know. Superposition isn't about confusion, it's about creativity. It's the universe keeping every door open until one must close, and even then, leaving the faint memory of all the others that could have been. The quantum world is full of surprises, but perhaps none is more fundamental or more misunderstood than uncertainty. In everyday life, uncertainty feels like ignorance. If you don't know where your keys are, it's not because their position is unknowable, it's because you haven't looked hard enough. But in quantum mechanics, uncertainty is not a matter of poor eyesight or bad equipment. It's woven into the very fabric of reality. Nature doesn't simply hide information from us. In some cases, that information doesn't even exist until we look for it. This principle was first clearly stated by Werner Heisenberg in the year 1927, and it's now known as the Heisenberg uncertainty principle. It says that for certain pairs of properties, like a particle's position and its momentum, you can never know both with perfect precision at the same time. The tighter you pin down one, the fuzzier the other becomes. If you measure an electron's position with extreme accuracy, its momentum becomes wildly uncertain. If you measure its momentum very precisely, its position spreads out into a cloud of probabilities. This isn't a problem with your tools, it's a built-in feature of how the universe operates on small scales. To see why, imagine a simple wave. The shorter its wavelength, the more precisely you can say where its peaks are. But short waves carry higher momentum. Long, smooth waves have a less certain position, but a more defined momentum. A particle's wave function, its mathematical description, follows this same logic. When you confine the particle's position, you combine many different wavelengths, which means many different momenta. When you allow its position to spread out, the wave becomes more uniform and its momentum more definite. The uncertainty between these two quantities isn't about measurement errors, it's a trade-off written into the mathematics of waves. This idea forces us to abandon the comforting image of a particle as a tiny billiard ball with well-defined position and speed. At the quantum level, such precision is impossible. Instead, a particle exists as a probability distribution, a blur of possibilities that only sharpens when measured, and even then, only partially. You can think of it like trying to describe a melody while it's still playing. You can know the song's overall tempo, momentum, or the exact note being struck, position, but not both with total certainty at the same instant. The act of narrowing one aspect necessarily blurs the other. This balance of knowledge extends beyond position and momentum. Other pairs of properties follow similar trade-offs. Energy and time, for example, are linked by an uncertainty relationship of their own. The shorter the time period you use to measure a system, the less precisely you can determine its energy. This might sound like an odd limitation, but it has powerful consequences. It explains why energy can briefly borrow from the vacuum, why particles can appear and vanish in empty space without breaking any rules. As long as these fluctuations occur quickly enough, they remain perfectly legal under the uncertainty principle. The universe, in a sense, allows itself tiny, temporary overdrafts of energy, provided they're repaid almost instantly. Uncertainty also applies to the components of spin, to angular momentum and to electric and magnetic fields. In every case, nature imposes a boundary on how sharply certain pairs can be defined. This limitation might sound like a weakness, but it's precisely what gives the quantum world its structure. Without uncertainty, atoms would be impossible. Electrons would spiral into their nuclei, and matter would collapse into a dense soup of energy. The uncertainty principle provides a kind of built-in cushion, a quantum pressure that prevents particles from occupying the same space too neatly. It's this gentle fuzziness that gives atoms their size, shapes chemistry, and keeps the universe from imploding. One of the most fascinating consequences of uncertainty is that it redefines what reality means. In classical physics, everything has definite properties whether or not we observe them. In quantum mechanics, many of those properties simply don't exist until they are measured. The particle doesn't secretly have a precise position and momentum waiting to be revealed. It genuinely lacks them until the act of measurement forces it to take on specific values. Observation doesn't just inform, it participates. This concept once unsettled even the pioneers of physics. Albert Einstein famously resisted the idea, insisting that God does not play dice. To him, uncertainty felt like an incomplete picture, a sign that quantum theory was missing something deeper and more deterministic. But decades of experiments have consistently shown that uncertainty isn't a symptom of ignorance. It's the universe's own handwriting, its natural grammar for describing the very small. One might think this intrinsic randomness would make the universe chaotic, but the opposite is true. When viewed statistically, quantum uncertainty produces astonishing precision. The spread of possibilities follows exact mathematical rules, and those rules make crystal clear predictions. Lasers, atomic clocks, transistors, and quantum sensors all depend on the reliable nature of quantum uncertainty. If the world were perfectly deterministic, these technologies wouldn't work. It's the very fuzziness of the microworld that allows them to exist. You can even see uncertainty in action in the energy levels of atoms. Electrons are not whirling around nuclei like planets around a sun. They exist in quantized orbitals, stable regions of probability that satisfy the uncertainty principle. The smaller an orbital, the more localized the electron, and the more uncertain its momentum. The balance between those uncertainties defines the structure of the atom itself. This is why electrons don't collapse inward. They cannot simultaneously have a precisely known position and momentum that would allow it. Quantum uncertainty creates a minimum radius, a safe zone that keeps the atom intact. The same logic applies to the stability of matter on a larger scale. Inside white dwarf stars and neutron stars, for instance, uncertainty in momentum prevents matter from collapsing under gravity's pull. When electrons are squeezed into smaller and smaller spaces, their momenta become increasingly uncertain, and thus, on average, extremely high. This creates a pressure known as degeneracy pressure, a quantum force strong enough to hold up an entire star. In this way, Heisenberg's principle helps prevent the cosmos from crushing itself into oblivion. Uncertainty even sneaks into the act of seeing itself. To observe something, you have to interact with it, bounce photons off it, or detect it through an electric field. But every photon that touches an electron imparts a tiny amount of momentum, changing what it was you were trying to measure. The sharper the image you want, the shorter the wavelength of light you need to use, and the more energy each photon carries, disturbing the system more strongly. There's no escaping this trade-off. It's not technological clumsiness, but a fundamental rule of the quantum game. Perhaps the most profound aspect of the uncertainty principle is how it reshapes our idea of knowledge. In a universe governed by uncertainty, perfect prediction is impossible, but that doesn't mean chaos. It means that probability, not precision, is the language of truth. When physicists calculate outcomes, they don't aim to know exactly what will happen. They aim to know the likelihoods, the shapes of possibility. And in those shapes lies extraordinary order. The quantum world doesn't promise certainties. It offers boundaries within which everything makes sense. Heisenberg's principle doesn't hide reality, it defines it. It shows that even the simplest act of existence involves balance. Every gain in knowledge comes at the cost of something else. And perhaps that's not so alien after all. Even in daily life, the more tightly we try to hold on to one thing, the more others slip away. Nature, it seems, plays by the same rule, only with better mathematics. So uncertainty isn't the enemy of knowledge, it's the quiet architecture that makes the universe both stable and alive. Beneath the precision of our instruments and the predictability of our world lies a gentle blur, a built-in softness that keeps reality from collapsing under its own weight. And in that balance between what can be known and what forever remains uncertain, the universe finds its rhythm. Measurement in the quantum world is one of those ideas that seems simple on the surface, but the deeper you look, the stranger it becomes. In classical physics, measurement is straightforward. You observe something that already exists, like checking the temperature of a cup of tea or the speed of a car. But in quantum mechanics, the act of measuring doesn't just reveal what was there, it helps decide what becomes real. Before measurement, a system can exist in a superposition of possibilities. After measurement, only one outcome remains. It's as if the universe flips a coin, but one weighted precisely according to the rules of quantum probability. When we measure a quantum system, we're forcing it to choose from a set of potential states, and the odds of each result are determined by something called the amplitude, a complex number describing how strongly that state contributes to the overall wave function. These amplitudes can interfere with one another, adding and cancelling in ways that shape the probabilities we observe. When the measurement happens, the wave function collapses into a single outcome, one snapshot from an infinite film reel of potential stories. What's remarkable is that while any single measurement seems random, the statistics of many repeated measurements are perfectly predictable. The randomness isn't chaotic, it's structured. Quantum theory doesn't tell us which individual event will occur, but it tells us the pattern that will emerge when billions of them do. It's like predicting the shape of a dice histogram. You can't know each roll, but you can know the average outcome with exquisite accuracy. This statistical precision is what gives quantum mechanics its power. The numbers it predicts match experiments to astonishing degrees, often to more than 10 decimal places. This probabilistic nature led to one of the most famous debates in science. Albert Einstein struggled with the idea that nature itself might be fundamentally random, famously declaring, "God does not play dice." To him, quantum mechanics was incomplete. Its probabilities reflected our ignorance, not the universe's uncertainty. But decades of experiments have shown that Einstein's hope for hidden variables was in vain. The randomness appears to be real, intrinsic, and irreducible. The universe does play dice, but with a consistency that would make any casino jealous. The measurement process also blurs the line between observer and observed. In everyday life, we imagine these as separate. The scientist looks through the microscope. The world sits on the slide. But quantum physics doesn't allow such a clean distinction. To measure a particle, you must interact with it, and that interaction inevitably changes it. The photon you use to see an electron transfers energy and momentum, disturbing the very thing you're trying to examine. The observer becomes part of the experiment, and the measuring device becomes entangled with the system. After measurement, they're no longer independent. They share information in a single, combined state. This idea inspired endless debate among the founders of quantum theory. Niels Bohr argued that we can never speak about a system's properties in isolation, only about the outcomes of measurements. Reality, he suggested, doesn't exist as definite values before we observe it. Instead, it exists as potentialities that solidify into facts through interaction. Others, like Schrödinger and Einstein, were less comfortable with that view. Schrödinger's thought experiment with his famous cat dramatized the tension. If a single atom can exist in superposition until measured, does that mean a cat linked to that atom must also be in limbo until someone opens the box? It was absurd, and yet the math implied just that. Over time, physicists began to realize that the key to understanding measurement lies in something called decoherence. In simple terms, decoherence describes how quantum systems lose their delicate superpositions when they interact with their surroundings. Every tiny collision with air molecules, every flicker of light, every vibration of atoms in the environment leaves a trace, entangling the system with the world. The result is that the interference patterns characteristic of quantum behavior disappear almost instantly. The system still obeys quantum laws, but its superpositions become inaccessible, buried in the complexity of countless microscopic interactions. To us it looks classical. Decoherence explains why tables don't exist in two places at once, why cats appear either awake or asleep, and why the macroscopic world seems stable and predictable. It bridges the gap between the quantum and the everyday. It doesn't require any mystical collapse. Instead, it shows that when quantum systems meet the messy reality of the world, their probabilities blur into the averages we call facts. It's not that measurement creates reality out of nothing. It's that reality, by its very nature, is a network of interactions, constantly forcing decisions about what can be observed. What makes measurement even more fascinating is that we can see its effects in controlled experiments. Physicists can delay the act of measurement in so-called delayed choice experiments, where they decide whether to observe a particle as a wave or a particle after it's already passed through an apparatus. Somehow, the particle's behavior still aligns with the choice, as if reality adjusts retroactively to fit the observation. It doesn't mean the future changes the past, but it does mean that the concept of a definite history, something classical physics takes for granted, starts to unravel at the quantum level. There's also the famous quantum eraser experiment, where scientists mark which path a photon takes through a pair of slits, destroying the interference pattern. But if that path information is later erased without ever being directly seen, the interference returns, as if the photon once again travelled both routes. The universe seems to keep its options open until the very end, and what counts as a measurement depends entirely on what information remains accessible. This is why physicists sometimes describe measurement not as an abrupt event, but as a transition from coherence to correlation. Before measurement, the quantum system holds many possible outcomes. During measurement, it becomes correlated with the measuring device, which in turn becomes correlated with its environment. Bit by bit, the web of relationships grows until one branch dominates, the one we perceive as reality. The other possibilities don't vanish, they're simply woven into patterns too subtle for us to detect. Despite the mysteries that remain, quantum measurement isn't mystical. It's precise, mathematical, and testable. The probabilities it governs have been confirmed in thousands of experiments, from photon polarization tests to quantum computing operations. Each time, the outcomes match the predictions of the theory to extraordinary accuracy. The quantum world may not tell us what will happen next, but it tells us exactly how likely each outcome is, and that's often enough to control it. In the end, measurement in quantum mechanics teaches a quiet lesson about participation. The universe doesn't unfold as a static film reel waiting to be watched. It's an active conversation between systems, each probing and influencing the other. Reality, at its smallest scales, isn't a fixed script. It's a series of negotiations, written in probabilities and read through interaction. When you look closely enough, even the simplest question, what happened, turns out to depend on how, when, and whether you chose to ask. And in that subtle dependence, somewhere between possibility and fact, lies the strange balance that allows the universe to be both unpredictable and perfectly consistent all at once. Entanglement is one of those ideas that feels like it was smuggled into physics from a science fiction story. It describes a connection so deep that two particles, once linked, seem to share a single state, no matter how far apart they travel. Change one, and the other responds instantly, not through space, but beyond it, as if distance has been quietly erased. Albert Einstein famously called this spooky action at a distance, a phrase that captures both his skepticism and the eerie elegance of the effect. To picture entanglement, imagine creating a pair of particles whose properties are perfectly correlated. For example, their total spin might always add up to 0. If one is measured to spin up, the other must spin down. When they separate, each particle carries no definite spin of its own, only the relationship that ties them together. Measure one, and the other's state becomes known instantly, even if it's light years away. This isn't communication because no usable signal travels between them, but it's an astonishing display of quantum unity, the idea that two objects can share a single, inseparable identity. The strange part is that, until measurement, neither particle possesses a definite value. They exist in a superposition of possibilities, bound by their shared wave function. When one is measured, the joint state collapses, and both results become real in perfect opposition. The outcome isn't predetermined, yet once chosen, it fits flawlessly with its partners. This defies our classical intuition, where information must move through space and time at finite speeds. In quantum mechanics, it's as if the two particles are aspects of the same system, their connection not limited by distance. Physicists spent decades arguing about whether these correlations were truly non-local or simply the result of hidden variables, unknown factors that predetermined the outcomes in ways we couldn't detect. Einstein, Podolsky, and Rosen famously raised this challenge in a 1935 paper suggesting that quantum mechanics must be incomplete. If the theory allowed such instantaneous effects, they reasoned, it couldn't describe reality as it truly is. Something deeper, some hidden mechanism, must be missing. Enter John Bell, an Irish physicist who in the 1960s formulated a way to test Einstein's suspicion. Bell derived mathematical inequalities, limits on how strong correlations could be if local hidden variables were responsible. If experiments ever showed correlations stronger than those limits, it would mean that no local, deterministic explanation could possibly account for them. And when the tests were finally performed, starting with Alana Speck's experiments in the 1980s and continuing with ever more precise setups, the results were clear. The quantum predictions won. The observed correlations were stronger than any local theory could allow. Nature, it seems, really does defy classical separation. Entanglement doesn't mean information travels faster than light. The results of measurements are still random. No observer can control which outcome appears, so no signal can be sent through the connection. But once both results are compared, the correlations emerge, as if two dice rolled on opposite sides of the galaxy always add up to the same number. The randomness of each roll remains untouched, yet the total is mysteriously synchronized. It's not about messages crossing space, it's about space itself not being the whole story. What's truly remarkable is that entanglement isn't rare or fragile, it's everywhere. It happens naturally in atoms, molecules, and even light beams. It's the glue that holds much of quantum mechanics together. In fact, entanglement can be thought of as the currency of the quantum world, a kind of invisible thread that allows systems to share information in ways classical physics can't match. And far from being a philosophical curiosity, it's now a tool engineers and scientists use deliberately. Quantum communication relies on entanglement to ensure security. In quantum key distribution, two parties share pairs of entangled photons. If anyone tries to eavesdrop, the act of measurement disturbs the system, breaking the correlations and revealing the intrusion. This isn't just theoretical. Real-world systems have already demonstrated quantum encryption over hundreds of kilometers of fiber and even between satellites and ground stations. Entanglement, once seen as spooky, now guards digital secrets. Quantum computers, too, depend on entanglement. Ordinary bits store information as zeros and ones, but quantum bits, or qubits, can exist in superpositions of both. Entanglement links qubits together so that operations on one affect the probabilities of others, enabling patterns of computation impossible for classical machines. It's this interdependence, the subtle dance of correlated states, that gives quantum computers their extraordinary potential power. Even the emerging field of quantum teleportation uses entanglement to transfer the state of one particle to another across space. This doesn't mean matter itself is sent, only the quantum information that defines it. By using a shared entangled pair and a few bits of classical communication, scientists can recreate an exact copy of a quantum state at a distant location. It's not faster than light travel, but it's the closest thing physics allows to moving information instantaneously. Entanglement also plays a quiet, essential role in the natural world. In photosynthesis, for instance, it may help plants transfer energy with near-perfect efficiency by keeping multiple molecular pathways correlated. In physics research, entangled particles are used to test the limits of relativity, measure gravitational effects on quantum systems, and probe the fundamental symmetry of the universe. Even black holes, those mysterious engines of gravity, may owe their connection to the quantum fabric of spacetime itself, with entanglement acting as the stitching that holds the cosmos together. Despite its weirdness, entanglement is one of the most precisely tested phenomena in science. Experiments have confirmed it over and over again, closing every loophole scientists could imagine. Photons, electrons, atoms, even large molecules, all have been entangled successfully, sometimes across distances of hundreds of kilometers. In 2017, researchers even demonstrated entanglement between a ground station on Earth and a satellite orbiting in space, proving that the quantum link can survive the vast distances and turbulence of the atmosphere. Still, entanglement forces us to rethink what it means for two things to be separate. The concept of locality, the idea that objects can only influence each other through contact or signals travelling between them, breaks down. The universe, at its deepest level, seems less like a collection of independent objects and more like a single, continuous web. Each particle, each atom, is a node in that web, its properties defined as much by its relationships as by itself. And yet, for all its philosophical weight, entanglement behaves with perfect obedience to the equations that describe it. It's not a loophole or a contradiction, it's the natural outcome of quantum theory's mathematics. The correlations are strong but never exploitable for instant messaging, mysterious but never chaotic. Nature allows connection without communication, coordination without contact, and certainty without cause. Einstein might have been unsettled by this spooky action, but modern physics has learned to live comfortably with it. What once seemed supernatural has become a daily tool in laboratories around the world. Entanglement, far from being an embarrassment to our understanding, is a testament to how deeply unified the universe really is. When two particles meet and part ways, they never fully let go of each other. Some invisible bond remains, woven into the laws of probability themselves. It's as though the universe keeps a quiet record of their meeting, an echo of shared existence that distance can't erase. In that subtle connection lies one of the most extraordinary truths of all, that separation, at the smallest scales, is an illusion, and everything, every atom, every spark of light, is part of the same intricate conversation. Spin is one of those concepts that sounds simple until you try to explain it. The name makes it sound as though subatomic particles are spinning like tiny planets, but that picture is misleading. Spin isn't motion through space. It's an intrinsic property, a kind of built-in angular momentum that doesn't rely on physical rotation. If an electron were truly spinning in the classical sense, its surface would have to move faster than the speed of light, which is impossible. Yet the particle behaves as if it carries a permanent internal twist. Spin is one of nature's subtle fingerprints, an invisible arrow built into every quantum object. The discovery of spin dates back to the early 1900s, when physicists noticed a strange doubling in atomic spectral lines. According to the best models of the time, certain transitions between energy levels should have produced single lines of light, yet they appeared as pairs. In 1925, two young Dutch physicists, George Uhlenbeck and Samuel Goudsmit, proposed that electrons must possess an intrinsic angular momentum, something distinct from their motion around the nucleus. Their idea explained the puzzling patterns instantly, and revealed an entirely new dimension of quantum behavior. Unlike ordinary angular momentum, which can take on any value depending on how fast or slow an object rotates, quantum spin comes in discrete chunks. It's quantized, meaning it can only take specific values, often expressed in multiples of Planck's constant divided by 2π. Electrons, protons, and neutrons each have a spin of 1/2, while photons, gluons, and other force-carrying particles have integer spin, such as 1 or 2. This difference divides the universe into two great families: Fermions, which have half-integer spin and make up matter, and bosons, which have integer spin and carry the forces that act between particles. Spin also comes with a curious rule. When you rotate an ordinary object by 360 degrees, it looks the same as before. But rotate an electron's quantum state by 360 degrees, and it doesn't come back to its original form. It picks up a minus sign. Only after a full 720-degree rotation does it return to its starting condition. It's a bizarre property that defies classical logic, but it's been verified in countless experiments. This strange two-turn symmetry lies at the heart of the mathematics describing all fermions. One of the most elegant demonstrations of spin came from the Stern-Gerlach experiment in 1922. Otto Stern and Walter Gerlach sent a beam of silver atoms through a non-uniform magnetic field. Classical physics predicted that the atom's tiny magnetic moments would orient randomly, producing a continuous smear on the detector. Instead, the beam split cleanly into two distinct spots. The silver atoms, each containing a single unpaired electron, had only two possible orientations of spin, up or down, nothing in between. This result shocked the scientific community. It showed that spin, like so many quantum quantities, doesn't vary smoothly but jumps between fixed states. This two-state nature of spin makes it an ideal candidate for storing information. In fact, modern quantum computers often use the spin of electrons, atomic nuclei, or photons as qubits, the quantum equivalents of bits. A classical bit can be either 0 or 1, but a spin qubit can exist in a superposition of both up and down, vastly expanding the computing landscape. By entangling multiple spins, quantum computers can perform calculations that would take classical machines longer than the age of the universe. Spin is also deeply tied to magnetism. Every electron acts like a tiny bar magnet because of its spin. In most materials, these little magnetic moments point in random directions, cancelling one another out. But in ferromagnetic substances like iron, cobalt, and nickel, the spins of countless electrons align in the same direction through quantum interactions known as exchange forces. When large regions of aligned spins form, they create magnetic domains, and when those domains line up, we get a magnet strong enough to hold a note to a refrigerator door. That familiar magnetism we experience every day, from compasses to hard drives, is simply quantum spin made visible. The role of spin extends far beyond magnets. It shapes chemistry itself. When two electrons occupy the same orbital in an atom, they must have opposite spins. This rule, the Pauli exclusion principle, arises directly from the fact that electrons are fermions. No two fermions can share the same quantum state. The exclusion principle explains why atoms have structure, why matter has volume, and why the periodic table exists in its layered form. Without spin, electrons would collapse into the lowest energy level, and all of chemistry would vanish. Spin even plays a role in the light that reaches your eyes. Photons, the carriers of electromagnetic radiation, have a spin of 1. But unlike electrons, their spin aligns with their direction of motion. producing what we call polarization. When you wear polarized sunglasses, you're filtering light based on its spin orientation. This shimmer on the surface of water or the glare from glass disappears because your lenses only allow photons of a certain polarization to pass through. Every time you tilt your head and watch the light change, you're interacting with quantum spin at a macroscopic scale. In particle physics, spin acts as a kind of cosmic classifier. It determines not only what a particle is but also how it behaves. Fermions with half-integer spin build up the material world by stacking in complex ways. Bosons with integer spin mediate forces, allowing fermions to communicate their presence. The Higgs boson, discovered in 2012, has spin 0, giving it a unique ability to endow other particles with mass. The photon spin makes electromagnetism work. The graviton, if it exists, would have spin 2, corresponding to the fabric of spacetime itself. Spin is one of those quantum features that hints at the underlying symmetry of the universe. It's connected to the concept of rotational invariance, the idea that the laws of physics don't change when you rotate your frame of reference. Mathematically, this is captured by something called spinor transformations, which describe how quantum states twist through space. Spinors are subtle creatures. They carry the memory of rotation, encoding how particles respond to changes in orientation. They're the reason why an electron's wave function needs 2 full turns to come back home. At human scale, spin's effects are invisible, but at quantum scales they dominate everything. In medical imaging, magnetic resonance imaging (MRI) machines exploit the spins of atomic nuclei. By aligning them in a magnetic field and then flipping them with radio pulses, MRI scanners create detailed pictures of the human body without a single incision. Each bright pixel in those images comes from nuclei relaxing back into alignment, releasing radio waves that reveal the intricate architecture of life. The same physics behind a simple magnet powers one of medicine's most important tools. Spin also underpins phenomena like superconductivity, where electrons form pairs with opposite spins, so-called Cooper pairs, that move through materials without resistance. It's even central to the field of spintronics, where information is stored and transmitted through spin orientation rather than the electric charge. Devices based on spintronics could one day outperform traditional electronics in speed and energy efficiency. So while the word spin might suggest something familiar, what it really represents is one of the universe's most fundamental forms of order. It's a hidden quantum compass inside every particle, guiding its behavior, dictating its interactions, and giving rise to nearly every magnetic and structural feature of matter, from the smallest electrons in an atom to the enormous magnetic fields of planets and galaxies. This same principle repeats. The universe may look vast and still, but deep down it's filled with countless invisible arrows, all spinning in quiet unison. And in those tiny quantum twirls lies the reason that everything, from the light in your eyes to the magnets on your fridge, works the way it does. Every particle in the universe belongs to one of 2 great families, fermions and bosons. At first glance they might seem like distant cousins, but the distinction between them defines nearly everything about how matter and energy behave. Fermions are the particles that make up matter, the solid stuff of the universe, while bosons are the carriers of forces, the messengers that tell fermions how to interact. The 2 families obey very different rules, and those rules are what make atoms stable, light coherent, and the cosmos as structured as it is. Fermions are the individualists of the quantum world. Electrons, protons, neutrons, quarks, each one refuses to share its exact quantum state with another. This principle is called the Pauli exclusion principle, named after the physicist Wolfgang Pauli, who proposed it in 1925. It states that no two identical fermions can occupy the same quantum state simultaneously. If one electron in an atom sits in a particular energy level with a specific spin, no other electron can take that exact combination. This simple rule shapes the architecture of everything around us. It's why electrons fill atoms in layers, why elements have distinct chemical properties, and why matter takes up space. Without exclusion, all electrons would collapse into the lowest energy level, atoms would shrink into nothing, and chemistry as we know it would vanish. This antisocial behavior of fermions gives rise to the incredible complexity of the periodic table. Hydrogen, helium, carbon, oxygen, all their differences stem from how electrons fill the available states around the nucleus. Every additional electron must find its own unique configuration, creating shells and subshells that determine how atoms bond and form molecules. Pauli's rule is also the reason you can't walk through walls. When you press your hand against a surface, the electrons in your skin are repelling the electrons in the solid object, not because of a direct mechanical push, but because quantum mechanics simply doesn't allow them to occupy the same space. The solidity of matter, the sensation of touch itself, is a direct consequence of fermions refusing to overlap. Bosons, on the other hand, are the extroverts of the particle world. They don't mind sharing states. In fact, they prefer it. Photons, gluons, and the W and Z particles of the weak force are all bosons, as is the famous Higgs boson discovered in 2012. Unlike fermions, multiple bosons can pile into the same quantum state, reinforcing one another's presence. This tendency to bunch together is what gives rise to some of the most remarkable phenomena in nature. Take light, for instance. When many photons of the same frequency and phase travel together, they create a coherent beam, a laser. The word laser actually stands for light amplification by stimulated emission of radiation, a process that relies entirely on bosonic behavior. Inside a laser, excited atoms are coaxed into emitting photons that are perfectly synchronized with those already present. Because photons are bosons, there's no restriction on how many can occupy the same state, so they cascade together, amplifying one another in perfect unison. The result is a narrow, intense beam of light capable of cutting metal, reading data from a disk, or guiding a spacecraft millions of kilometers away. Without the cooperative nature of bosons, the concept of a laser would be impossible. This fundamental difference, fermions keeping their distance, bosons clustering together, extends to the structure of the universe itself. The behavior of fermions gives matter its stability and resistance to compression. It's what keeps white dwarf stars from collapsing, as the electrons within them generate a quantum pressure when squeezed too tightly. The collective alignment of fermionic spins defines magnetism, and the arrangement of fermions in solids governs everything from conductivity to hardness. Bosons, meanwhile, weave the forces that connect those particles. Photons carry electromagnetism, gluons hold atomic nuclei together through the strong force, and the Higgs field gives mass to particles by interacting with them everywhere in space. The distinction between these two families isn't arbitrary. It comes down to spin, that intrinsic quantum twist each particle carries. Fermions have half-integer spin values, like 1/2 or 3/2, while bosons have whole number spins, such as 0 or 1. That single difference changes the mathematical symmetry of their wave functions, and dictates whether particles repel or congregate. It's not a personality trait, but a deep rule of nature, built into the fabric of quantum statistics. Fermions follow what's called Fermi-Dirac statistics, which forbid duplicates in the same state. Bosons obey Bose-Einstein statistics, which encourage them to gather. This bosonic crowding leads to another marvel, the Bose-Einstein condensate. Predicted by Satyendra Nath Bose and Albert Einstein in the 1920s, it was first created in laboratories in 1995. When a gas of bosonic atoms is cooled to near absolute zero, the particles lose their individual identities and collapse into a single quantum state, behaving like one giant atom. It's a state of matter where the quantum world becomes visible on a macroscopic scale, with atoms marching in perfect synchrony. If fermions are the reason the universe doesn't flatten, bosons are the reason it can occasionally act like a symphony. The antisocial nature of fermions also explains a curious phenomenon known as degeneracy pressure. When matter is squeezed to extreme densities, such as in the core of a dying star, the electrons can't all occupy the lower states. The exclusion principle forces some to higher and higher energy levels, creating pressure that resists further compression. This is what halts the collapse of white dwarf stars, balancing gravity with pure quantum mechanics. When that pressure is overcome, even electrons merge with protons to form neutrons, another kind of fermion, producing neutron stars, where the same exclusion rules between neutrons hold the stellar corpse up against unimaginable gravity. Bosons, in contrast, tend to be the mediators of communication. They allow fermions to interact while never getting in the way themselves. The photon lets charged particles exchange electromagnetic force. The gluon binds quarks inside protons and neutrons, and the graviton, if it exists, would carry the gravitational force through space-time. They don't obey the exclusion principle because they're not matter in the conventional sense. They're the threads of interaction, the fields that connect everything else. In the quantum world, these two species, fermions and bosons, complement each other perfectly. Fermions create the universe's stuff, while bosons choreograph its behavior. One builds structure through refusal, the other builds harmony through sharing. Their interplay is what gives rise to every physical phenomenon, from the rigidity of rock to the warmth of sunlight. Without fermions, there would be no matter. Without bosons, matter would never know how to interact. Even at cosmic scale, this division still shapes reality. The stars that shine, the atoms in your body, the photons streaming through space, all of it arises from the delicate balance between particles that stay apart and those that come together. Every element in existence, every burst of light from a distant galaxy, is a quiet duet between these two families, each following its own timeless rule. So while the universe may look infinitely varied, beneath all its complexity lies a simple truth. There are only two kinds of building blocks. One kind insists on individuality, and the other thrives on unity. And from their endless negotiation, from the Fermionic resistance that gives matter form to the bosonic cooperation that spreads energy through space, the entire structure of existence emerges. In the modern view of physics, everything, every particle, every force, every flicker of energy is an expression of something deeper, fields. Not fields like the kind you walk through, but vast invisible entities that fill all of space, rippling and interacting everywhere at once. A field isn't confined to a location. It's a kind of presence spread throughout the entire universe. And what we call particles are not little dots zipping through space, but tiny disturbances in those fields, quantized ripples that behave like discrete bits of matter or light. Take light itself. It's not a stream of miniature bullets racing through the void, but a wave in the electromagnetic field. That field exists everywhere, even in darkness, vibrating with a quiet potential that can spring into motion when energy is added. A single photon is the smallest possible vibration of this field, a packet of energy with just enough amplitude to be counted as one unit. Every beam of sunlight, every radio wave, every colour you've ever seen is made of countless electromagnetic ripples rising and falling in concert. Matter follows the same rule. Electrons, protons and quarks, the building blocks of atoms, are not standalone objects drifting through space, but excitations in their own underlying fields. There's an electron field that spans the entire universe, and every electron everywhere is simply a localized excitation within it. When you hold up your hand, the electrons making up your skin are just tiny peaks in the same vast field that stretches all the way to the edge of the cosmos. They look and feel distinct because the excitations are stable and confined, like the plucked notes of a tightly tuned instrument. Each type of fundamental particle has its own field, one for electrons, another for quarks, others for neutrinos, muons, and so on. The photon field carries electromagnetism. The gluon field binds quarks together inside protons and neutrons. There are fields for the weak nuclear force, for gravity, if it can be unified, and even for the Higgs boson, whose field gives mass to other particles by resisting their motion through it. These fields don't switch off when nothing seems to be happening. They're always there, quietly interacting, shaping reality beneath the surface of perception. Interactions between particles, what we usually call forces, are simply exchanges of energy between fields. When two electrons repel each other, it's not because invisible hands push them apart. It's because they disturb the electromagnetic field in each other's vicinity, and the field responds by transferring momentum via photons, the quanta of the electromagnetic interaction. When a quark feels the strong nuclear force, it's exchanging gluons, the quanta of the gluon field, with its neighbours. The same logic applies everywhere. Every fundamental force arises from fields talking to one another, passing information through their ripples. One of the most fascinating consequences of quantum field theory is that the vacuum itself, the so-called empty space between particles, isn't empty at all. Even when stripped of all matter and energy, the fields remain. They can't sit perfectly still. Quantum mechanics forbids it. Instead, they tremble with restless zero-point energy, their values fluctuating randomly at every point in space. Particles can briefly appear and disappear in these fluctuations, borrowing energy from the vacuum before fading away. These are called virtual particles, and while they can't be observed directly, their effects can be measured. The small corrections they produce to the energy levels of atoms have been detected with astonishing precision, confirming that the vacuum is far from inert. This something-from-nothing behaviour might sound absurd, but it has real consequences. It gives rise to the Casimir effect, where two uncharged metal plates placed very close together in a vacuum attract each other because they restrict which virtual waves can exist between them. It also contributes to the cosmological constant, the tiny but measurable energy density of empty space that drives the universe's accelerated expansion. The fact that emptiness has energy is one of the most profound discoveries of modern physics, reshaping our understanding of both the microscopic world and the cosmos as a whole. The elegance of the field concept is that it unites all particles and forces under one mathematical framework. In classical physics, we had separate rules for matter and for energy, for waves and for particles. Quantum field theory merged them into a single language. Matter is energy, waves are particles. The difference lies in how the field vibrates. High frequency, high energy vibrations manifest as massive particles, while gentle oscillations show up as light or radiation. The entire universe becomes a symphony of interacting fields, its complexity built from simple harmonies that play across all of space-time. Even the concept of identity changes in this picture. When two electrons collide and scatter, there's no meaningful way to say which one is which afterward. They're indistinguishable excitations of the same underlying field. In a sense, there's only one electron field, endlessly rippling, and every electron we ever detect is a temporary crest in that single, universal ocean. The particles don't have individuality. What matters is the pattern of vibration, the specific arrangement of energy in the field. This is why all electrons are identical, no matter where or when you find them. Nature doesn't make them one by one, it makes them as waves of the same song. The quantum field perspective also explains why creation and annihilation of particles are so natural in high-energy physics. When energy is concentrated enough, it can excite the field strongly enough to produce new ripples, new particles. When those ripples cancel out, the energy returns to the field. Nothing is ever lost, it simply changes form. In particle accelerators, physicists smash particles together to create intense field disturbances, coaxing new excitations into existence, briefly revealing the hidden symmetries of the universe. These fields are also inherently quantum, meaning their vibrations come in discrete steps, quanta, rather than continuous waves. The mathematics that governs them, known as the Standard Model of Particle Physics, has been tested in countless experiments and has never failed. It predicts with extraordinary precision the behavior of subatomic particles, from the magnetism of electrons to the decay rates of exotic mesons. Even so, physicists know it's incomplete. The fields we've mapped so far explain nearly everything we can observe, but they don't include gravity, and they leave questions about dark matter, dark energy, and the early universe unanswered. The quest for a deeper understanding, perhaps through string theory or quantum gravity, is really a search for a more fundamental kind of field. It's an attempt to uncover the ultimate medium that gives rise to all others, the single framework that might weave together space, time, matter, and energy into one consistent whole. But even without that final unification, the field view offers a deeply satisfying picture of reality. It tells us that the universe is not a collection of isolated objects bumping into each other in empty space. It's a continuous, dynamic tapestry of vibrations where every point is alive with possibility. Even in the darkest vacuum, every field hums faintly, carrying the echoes of everything that has ever existed and everything that ever could. When you look up at the night sky, what seems like empty darkness between the stars is anything but. Every inch of it is filled with fields, electromagnetic, gravitational, nuclear, whispering their invisible conversations across the cosmos. The stars, the planets, even you are simply denser, more organized notes in that grand, unseen symphony. The universe isn't made of things, it's made of patterns, waves and fields, woven together into the song of existence itself. At first glance, empty space seems like the most boring thing imaginable. A void, a total absence of matter and energy. But in the quantum world, nothing is never truly nothing. Even the deepest vacuum, stripped of every atom, every photon, every trace of heat, still seethes with invisible activity. Space itself trembles with fluctuations, as quantum fields constantly shift and flicker. It's a kind of cosmic background hum, so faint and so fast that it usually goes unnoticed, yet powerful enough to shape the universe itself. In classical physics, a vacuum is the simplest possible state, a region completely devoid of particles. But quantum field theory doesn't allow perfect stillness. According to the uncertainty principle, you can't know both the exact energy and the exact duration of a state at the same time. If a region of space were truly at zero energy, its lifetime would have to be infinite, and the universe doesn't seem to permit infinity in practice. Instead, fields in empty space constantly borrow and repay tiny amounts of energy, creating fleeting disturbances that appear as particle-antiparticle pairs. These pairs form spontaneously, live for unimaginably short times, and then annihilate, restoring the energy they borrowed. These ghostly events are called vacuum fluctuations, and though they sound like science fiction, their effects are measurable. In fact, they're essential to the stability of the quantum world. Without these fluctuations, the electromagnetic field would fall silent, atoms would collapse, and forces would behave very differently. The quantum vacuum isn't a stage on which physics happens. It's an active participant in every process that occurs. When a particle and its antiparticle briefly pop into existence, they behave just like their long-lived counterparts, exerting tiny forces before disappearing again. One famous consequence of this is the Lamb shift, discovered in 1947 by physicist Willis Lamb. By measuring the energy levels of electrons in hydrogen with extreme precision, he found a small discrepancy that classical quantum mechanics couldn't explain. The missing ingredient turned out to be the restless vacuum itself. The fluctuating electromagnetic field slightly perturbs the orbiting electron, nudging its energy just enough to be detected. This subtle shift was one of the first pieces of direct evidence that empty space is far from empty. Another striking manifestation of the vacuum's energy is the Casimir effect, first predicted in 1948 by Dutch physicist Hendrik Casimir. Imagine two uncharged metal plates placed very close together in a vacuum, just a few nanometers apart. According to quantum theory, the electromagnetic field inside and outside the plates can support certain modes of vibration, like the harmonics of a violin string. But between the plates, only waves that fit exactly between them are allowed. That means there are slightly fewer vacuum fluctuations in the narrow gap than in the space outside. The imbalance produces a tiny pressure, pushing the plates together as if an invisible hand were squeezing them. The force is incredibly small, but it has been measured many times in the lab. It's a quiet reminder that the vacuum itself can exert a real, physical push. This same restless activity helps explain some of the most puzzling phenomena in the cosmos. The expansion of the universe, for example, appears to be accelerating, a discovery awarded the Nobel Prize in 2011. The leading explanation involves vacuum energy, the cumulative effect of all those quantum fluctuations adding up to a small but persistent outward pressure. In theory, the total vacuum energy should be immense, far greater than anything we observe, but for reasons still not understood, it mostly cancels itself out, leaving behind a faint residue that drives cosmic acceleration. This mismatch between theoretical prediction and observation is known as the cosmological constant problem, and it remains one of the biggest unsolved mysteries in physics, Even black holes aren't immune to the vacuum's mischief. In the 1970s, Stephen Hawking showed that quantum fluctuations near the event horizon can create real particles. When a particle-antiparticle pair appears right at the edge, one may fall into the black hole while the other escapes, carrying energy away. To an outside observer, it looks as though the black hole is slowly radiating heat, a process now called Hawking radiation. Over immense timescales, this radiation can cause a black hole to lose mass and eventually evaporate entirely. It's a breathtaking example of how the so-called vacuum can rewrite the fate of some of the universe's most extreme objects. What's perhaps most astonishing about all this is how precisely these effects can be measured. The corrections caused by vacuum fluctuations have been verified in experiments that agree with theory to 1 part in a trillion. When physicists calculate the magnetic moment of the electron, a measure of how strongly it behaves like a tiny magnet, the contribution from the vacuum must be included to get the right answer. Without it, the prediction would fail. That level of agreement is a triumph not just of measurement, but of understanding. It shows that even our emptiness obeys precise, elegant rules. The vacuum's restlessness also carries a philosophical weight. It blurs the line between something and nothing, between existence and absence. When quantum fields fluctuate, they create a sea of potentiality from which reality continually emerges. Every photon of light, every atom of matter, every spark of energy was, in some sense, born from this churning background. The Big Bang itself might have been a magnified version of the same phenomenon, a fluctuation that refused to vanish, inflating into a universe instead of fading back into silence. It's also worth noting that the vacuum's energy isn't uniform. In quantum chromodynamics, the theory describing the strong nuclear force, the vacuum is filled with fluctuating fields of quarks and gluons that shape the mass of protons and neutrons. In that sense, most of the mass of ordinary matter doesn't come from the particles themselves, but from the restless energy of the vacuum surrounding them. When you lift a stone, most of its weight comes not from solid matter, but from quantum emptiness bound in motion. On human scales, these effects are imperceptible. The room around you feels still and quiet, yet at the microscopic level, every cubic centimetre of space is buzzing with virtual particles appearing and vanishing at speeds faster than thought. The vacuum isn't a void. It's the foundation of reality, an invisible ocean whose waves build everything that floats above it. When physicists talk about the vacuum, they don't mean nothing. They mean the ground state of all fields, the lowest possible energy configuration the universe allows. Even at that minimum, fluctuations persist. It's like an ocean that can never be perfectly calm. There's always some motion, some rippling beneath the surface. If you could somehow remove every atom, every photon, every ounce of thermal energy from a region of space, it would still hum faintly with quantum whispers. That hum is the heartbeat of the universe. It's strange to think that everything, from galaxies to sunlight to our own consciousness, arises from a vacuum that refuses to be still. The universe doesn't emerge from silence, it emerges from restless equilibrium, a ceaseless shimmer that defines what empty really means. Nothingness, it turns out, is just another form of something, one that quietly sustains the existence of everything. At the heart of every atom lies one of the most important discoveries in all of science. Energy comes in steps, not slopes. Electrons can't just orbit a nucleus at any random distance. They can only occupy certain, specific energy levels. This simple rule, called quantization, is what keeps the universe from falling apart. It's the reason atoms are stable, the reason light shines in colours, and the reason chemistry has any structure at all. Without it, matter would blur into chaos, and everything we know would dissolve into an unbroken sea of energy. The idea of quantized energy was first proposed in the early 1900s, when Max Planck was trying to solve a riddle about heat and light. Experiments showed that hot objects didn't radiate energy continuously. Instead, their colours shifted in predictable ways as they warmed up. Classical physics couldn't explain this. It predicted that hotter objects should glow infinitely bright in the ultraviolet, a disaster known as the ultraviolet catastrophe. Planck found that he could fix the problem by assuming that energy was released in discrete packets, or quanta proportional to the frequency of light. It was a bold mathematical trick at the time, but it worked. A few years later, Albert Einstein applied Planck's idea to light itself. He showed that light sometimes behaved as if it were made of individual particles, photons, each carrying a precise quantum of energy. That leap of logic explained the photoelectric effect, where light knocks electrons free from metal surfaces. Only photons above a certain frequency had enough energy to do it, no matter how bright the light was. It was a clear sign that nature wasn't continuous but granular, built from tiny, countable units of energy. Nowhere is this more evident than inside atoms. When an electron orbits a nucleus, it's bound by the attraction between negative and positive charge. According to classical physics, the electron should be able to orbit at any distance, radiating energy continuously as it spirals inward until it crashes into the nucleus. But that doesn't happen. Atoms are stable, and electrons stay suspended in neat, well-defined orbits. Niels Bohr solved the puzzle in 1913 by proposing that electrons could only occupy certain allowed energy levels, specific rungs on an atomic ladder. To move between these rungs, they must absorb or emit a precise amount of energy in the form of a photon. That simple picture gave rise to one of the most beautiful signatures in all of science: atomic spectra. When you heat a gas or shine light through it, the atoms absorb or emit light only at particular wavelengths. Viewed through a prism, these appear as bright or dark lines, like barcodes unique to each element. Hydrogen's lines form a simple pattern of reds and blues. Helium's are more complex. Iron's lines sprawl across the spectrum like tangled piano keys. These spectral fingerprints allow astronomers to identify the chemical makeup of distant stars and galaxies, even millions of light-years away. Every point of light in the night sky carries a record of quantum energy steps imprinted upon it. Quantization doesn't just determine the color of light, it dictates the structure of matter itself. Each electron in an atom must find an available energy level, and no two can share the same one with the same spin, thanks to the Pauli exclusion principle. This stacking of electrons in quantized shells gives rise to the periodic table, where elements repeat in predictable patterns. Helium, neon, and argon, for example, are stable, noble gases because their outermost electron shells are full. Sodium and potassium, with one extra electron in a new shell, are reactive because that electron can easily jump between energy levels. Chemistry, in all its diversity, is simply the choreography of electrons moving up and down the quantized staircase of energy. Each of those jumps releases or absorbs photons with energies corresponding to the gap between levels. Small jumps produce low-energy light, like infrared or red. Large jumps create high-energy ultraviolet or even X-rays. In the sun's core, for instance, quantized transitions between atomic and nuclear states govern how energy moves outward, shaping the star's light and temperature. Even neon signs and fluorescent lamps rely on this principle. Electricity excites electrons to higher levels, and as they fall back they emit light of characteristic colours: red for neon, blue for mercury vapour, green for argon. Every glowing city skyline is a silent testimony to quantum steps. The concept of quantized energy extends beyond atoms into the world of molecules and solids. In molecules, the same rules apply to vibrations and rotations. Bonds between atoms can stretch or twist only in discrete modes, each with its own quantized energy. That's why water vapor absorbs infrared light at specific wavelengths, giving Earth's atmosphere its unique fingerprint in climate models. In solids, electrons occupy bands of allowed energies, separated by forbidden gaps. The size of those gaps determines whether a material is a conductor, an insulator, or a semiconductor. Without quantized bands, computers, LEDs, and nearly every modern technology would be impossible. Even sound waves inside solids, called phonons, are quantized vibrations of the atomic lattice. These phonons explain why specific heat in materials changes with temperature, and why thermal conduction varies so widely between substances. The same mathematics that describes electrons in atoms also describes the vibrations that carry sound, heat, and even superconductivity. The entire modern world of electronics, chemistry, and materials science rests on the quiet, orderly discreteness that quantization imposes on energy. It might seem strange that nature would prefer steps to slopes, but quantization offers stability. If energy were continuous, even the smallest disturbance could drain or add energy endlessly, destabilizing every structure. Quantized systems, on the other hand, have well-defined ground states, the lowest possible energy they can possess. Once electrons settle there, they can't fall any further. The universe's preference for discrete levels is the reason atoms endure and matter persists. Quantization acts as a safety net, preventing collapse by setting hard floors and ceilings for energy exchange. At a deeper level, quantization reflects the wave nature of everything. Just as a guitar string can only vibrate in specific standing wave modes, electrons trapped around a nucleus can only form wave patterns that fit perfectly within the atomic boundary. These standing waves correspond to discrete energy levels. When an electron transitions between them, it's like the string jumping from one note to another. The music of the atom is a literal symphony of quantum harmonics, with every element playing its own unique scale. This discretization also explains why quantum systems behave so predictably in experiments. The colors of light emitted by hydrogen, measured and catalogued more than a century ago, match the predictions of quantum mechanics to astonishing precision. It's one of the most thoroughly tested aspects of all science. Every laser, every LED, every atomic clock operates on the principle that energy changes in fixed steps. Even time itself, as measured by cesium clocks, depends on counting the oscillations between two specific quantized states of cesium atoms. The idea of quantized energy might sound abstract, but it defines nearly every experience of light and colour in our daily lives. The blue of the sky, the red of a sunset, the green of leaves, they all arise from electrons interacting with photons of specific energies, absorbing some and reflecting others. When you look at a rainbow, you're seeing nature's energy ladder made visible, each hue corresponding to a distinct quantum transition. The discovery that energy comes in packets was one of the greatest intellectual revolutions in human history. It forced us to abandon the comforting smoothness of classical physics and embrace a world that changes in sudden, discrete leaps. Yet within those leaps lies order, precision, and beauty. Every atom's stability, every chemical bond, every flash of light is a tiny celebration of quantization, nature's quiet insistence that even energy, the most fluid thing imaginable, must still obey the rhythm of steps. At its core, quantized energy reminds us that the universe is both continuous and granular, a flowing sea built from indivisible ripples. And it's in those ripples, those tiny leaps between possibilities, that the difference between chaos and structure, darkness and light, truly begins. The story of quantum physics isn't just told through equations and theories, it's written in experiments that change the way we see reality. Each discovery chipped away at the comfortable assumptions of classical physics and replaced them with something far stranger, yet far more accurate. From beams of light knocking electrons free to single particles painting interference patterns one by one, these experiments didn't just reveal facts, they revealed that the universe is far weirder than anyone expected. At the dawn of the 20th century, physicists thought they understood light. It was a wave, beautiful, continuous and predictable. Then the photoelectric effect arrived like a crack in that certainty. When light shines on a metal surface, it can eject electrons, as if knocking them loose. Classical physics predicted that brighter light should always release more electrons, regardless of colour. But that wasn't what experiments showed. Only light above a certain frequency could eject electrons, and increasing brightness below that threshold did nothing. It didn't matter how intense a red beam was, it simply couldn't dislodge an electron. Albert Einstein, in 1905, made the daring suggestion that light's energy wasn't spread smoothly, but carried in discrete packets, quanta. Each photon had an energy proportional to its frequency, so blue light carried more energy per photon than red light. The photoelectric effect proved that light could behave like a particle, not just a wave. For that insight, Einstein won the Nobel Prize, and the wave-particle duality of light became one of the first great pillars of quantum theory. But nature wasn't done turning our intuitions upside down. If light could act like a particle, could particles also act like waves? In 1927, physicists Clinton Davison and Lester Germer were investigating how electrons scattered off a nickel crystal when they found a pattern that shouldn't exist. Bright and dark fringes of intensity, just like the interference patterns made by light waves. Their discovery confirmed Louis de Broglie's bold prediction that matter has wave-like properties. Electrons weren't tiny, solid marbles. They were ripples in a quantum sea, capable of interfering and diffracting just like light. That revelation inspired one of the most haunting experiments in all of physics, the double-slit experiment, performed with single particles. When light passes through two narrow slits, it creates a pattern of bright and dark bands on a screen, the hallmark of wave interference. But when scientists sent individual photons or even individual electrons through the slits one at a time, the same pattern slowly emerged. Each particle seemed to interfere with itself, as though it had gone through both slits simultaneously. Yet, if detectors were placed to determine which slit the particle actually passed through, the interference vanished, replaced by two distinct stripes, as if the particle had made up its mind. The conclusion was inescapable. Observation changes outcome. Reality doesn't decide what happened until it's forced to. This experiment has been repeated in countless variations, using atoms, molecules, and even large organic compounds, and the result never fails to astonish. The universe, it seems, only settles into one version of events when it's observed. Until then, everything remains in superposition, a haze of possibilities waiting to become real. The double-slit experiment isn't just a demonstration of wave-particle duality. It's a mirror reflecting the strange relationship between knowledge and existence itself. As physicists delved deeper into the quantum realm, they stumbled upon something even more counterintuitive: entanglement. The idea that two particles could remain linked across distance, sharing properties in ways that defied classical logic, was deeply unsettling. Einstein dismissed it as spooky action at a distance, convinced that hidden variables must exist to explain the correlations. In the 1960s, John Bell put that idea to the test with a series of inequalities, mathematical limits that any hidden variable theory would have to obey. Over the next few decades, experimentalists like Alain Aspect refined the technology to test Bell's inequalities using entangled photons. The results were stunning. Quantum mechanics predicted correlations stronger than any local hidden variable model could allow, and that's exactly what was observed. Repeated experiments since then, using ever more precise detectors and closing every possible loophole, have confirmed the result. The universe truly does exhibit non-local correlations. Entangled particles behave as if they share a single unified state, even when separated by vast distances. Reality, at its deepest level, isn't built for isolated parts, but from relationships that stretch across space. Those same correlations now serve as the foundation for quantum technology. Quantum communication, quantum computing, and quantum cryptography all rely on the strange power of entanglement that Bell's experiments helped confirm. What began as a philosophical challenge to the completeness of quantum mechanics became one of its most practical and astonishingly accurate tools. As the 20th century unfolded, the experiments became subtler and more precise, probing the quantum world with almost unimaginable sensitivity. One of the most delicate demonstrations of quantum effects at the macroscopic level is found in devices called squids, superconducting quantum interference devices. A squid is essentially a loop of superconducting material interrupted by one or more thin barriers known as Josephson junctions. When cooled to near absolute zero, electrons inside the superconductor form pairs that behave like a single quantum entity, flowing without resistance. The current in the loop can travel in both directions at once, a superposition of two opposing flows. By measuring the interference between these quantum states, squids can detect changes in magnetic fields as small as a few trillionths of a Tesla, sensitive enough to pick up the magnetic activity of the human brain or the faint whispers of cosmic phenomena. They are living proof that quantum mechanics isn't confined to the microscopic world. With enough care and isolation, even macroscopic systems can display the coherence and interference once thought to belong only to single atoms. Each of these experiments, from Einstein's photoelectric effect to modern squids, pushed the boundary of what physicists believed was possible. They showed that the quantum world isn't just an abstraction. It's the engine of reality, governing every spark of light and every atom of matter. What's most striking is how the quantum rules always hold, no matter how strange the setup. Whether it's electrons diffracting through crystals or photons choosing paths based on future measurements, the outcomes match the predictions of quantum theory with eerie precision. These iconic experiments didn't just test equations, they forced humanity to rethink its understanding of the universe. They taught us that light is both wave and particle, that matter shares the same dual nature, that observation shapes outcomes, and that even emptiness is alive with connection. The quantum world may be strange, but it's also astonishingly consistent, revealing the same truth again and again. Reality at its smallest scales is woven not from things but from probabilities, patterns, and relationships. If classical physics was about discovering how the universe works, quantum experiments revealed why it feels so mysterious. The more carefully we look, the clearer it becomes that the act of looking is part of the story. Every click of a detector, every photon that hits a screen, every signal from a squid is another reminder that nature doesn't reveal herself passively. She participates. And in that subtle partnership between observer and observed, the universe continues to perform its most dazzling trick, turning possibility into reality, one quantum at a time. In the classical world, barriers are simple things. A ball can't roll through a wall, a car can't pass through a mountain, and a person can't walk through glass unless something breaks. But in the quantum world, rules like can't become less absolute. Particles can, and often do, pass straight through barriers they shouldn't be able to cross. It's called quantum tunneling, and it's one of the strangest and most consequential effects in the universe. To understand tunneling, it helps to start with how quantum particles behave. An electron, for instance, isn't a point-like marble following a single path. It's a wave of probability spread out in space. Where classical physics would assign it a definite position and energy, quantum mechanics describes it as a cloud of possibilities. When such a wave encounters a barrier, say, a region of higher potential energy, it doesn't just stop. Part of the wave reflects back, but part of it seeps through, fading as it goes. If the barrier is thin enough or the energy high enough, the wave can emerge on the other side, even though classically the particle doesn't have enough energy to climb over. It's as if the universe occasionally allows particles to take shortcuts through walls, but only according to precise mathematical probabilities. The particle doesn't punch a hole through the barrier or dig under it. It simply exists as a wave that, against all odds, continues on the far side. And yet, this isn't magic. It's the natural outcome of the Schrödinger equation, the rule book that governs all quantum motion. Though it may sound like an oddity confined to theory, tunneling is at work all around us, and even above us. The light of the sun, for example, owes its very existence to tunneling. Deep within the sun's core, hydrogen nuclei collide at immense speeds and temperatures, but even there, they shouldn't have enough energy to overcome the strong electrical repulsion between their positive charges. Classically, fusion shouldn't happen, yet it does, constantly, because quantum tunneling allows protons to slip through the energy barrier and fuse together. Without tunneling, stars would never ignite, and the universe would be dark, cold, and lifeless. Every ray of sunlight, every star in the night sky, is a quiet celebration of the fact that the quantum world bends the rules of probability just enough to keep creation going. Here on Earth, tunneling has become one of our most powerful scientific tools. In 1981, physicists Gerd Binnig and Heinrich Rohrer built the Scanning Tunneling Microscope, or STM, an instrument so sensitive it can image individual atoms. The device works by bringing an ultra-fine metal tip within a few nanometers of a surface. Even though the tip doesn't physically touch the sample, electrons can tunnel across the tiny gap, creating a measurable current. The strength of that current depends on the distance between the tip and the surface, changing exponentially with even the smallest movements. By scanning the tip across the sample and recording the current, scientists can map out atomic landscapes in exquisite detail. The STM opened a new era of nanotechnology, allowing researchers not only to see atoms but to manipulate them one by one. Tunneling is also behind one of nature's more mysterious processes, radioactive decay. In certain unstable nuclei, particles like alpha particles are trapped by strong nuclear forces inside an energy barrier. Classically, they should stay confined forever. But quantum mechanics gives them a chance, small but non-zero, to tunnel through that barrier and escape. This is how many radioactive elements decay over time, their lifetimes governed by the probability of tunneling. The thicker the barrier, the slower the decay. That's why some isotopes vanish in seconds, while others endure for billions of years. The steady ticking of radioactive clocks, used to date rocks and fossils, is a direct result of quantum particles slipping through energy walls, one improbable event at a time. In electronics, tunneling shows up in surprising ways too. Devices called tunnel diodes take advantage of it to achieve extraordinary speeds. In a tunnel diode, electrons move through a very thin insulating layer between two conductive regions. Because of tunneling, they can pass through the barrier instead of going over it, allowing the device to switch states almost instantaneously. This makes tunnel diodes incredibly fast and efficient, with applications in high-frequency oscillators and advanced circuits. Another device, the Josephson junction, uses tunneling between superconductors to create precise voltage standards and ultra-sensitive magnetometers, the same principle behind squids used in measuring the tiniest magnetic fields. Tunneling isn't confined to electrons and protons, it happens in chemistry and biology too. In certain chemical reactions, atoms can rearrange in ways that would require more energy than seems available, unless quantum tunneling steps in. Hydrogen, being light and wave-like, can tunnel through energy barriers in enzyme reactions, speeding up biochemical processes in ways classical chemistry can't fully explain. Some researchers even suspect tunneling plays a role in photosynthesis, helping plants move energy efficiently through molecular networks. In a sense, life itself may rely on the same quantum trick that powers stars. One of the strangest aspects of tunneling is that it challenges our sense of cause and time. A quantum particle doesn't take a definite path through the barrier, nor can we say how long it spends there. Measurements suggest the process can occur faster than light would travel across the same distance. Though this doesn't violate relativity, no usable information is transmitted faster than light. Still, the implication is eerie. Tunneling seems to operate outside our ordinary understanding of motion. The particle isn't really moving through the barrier at all. It's just that the probabilities of where it can exist happen to leak through to the other side. The mathematics behind tunneling reveals that even impossibilities have degrees. The thicker the barrier and the lower the energy, the smaller the probability of transmission. But smaller in quantum mechanics doesn't mean never. Given enough particles and enough time, even the most improbable event will eventually occur. That's why quantum tunneling isn't a rare exception. It's a constant background process shaping everything from nuclear reactions to electronic signals. What's remarkable is how predictably this improbable effect behaves. The same equations that describe tunneling inside a silicon chip also describe it inside the heart of a star. It's one of the unifying features of quantum physics, an effect that stretches from the smallest scales to the grandest cosmic engines. It doesn't defy the laws of physics, it is one of them, written into the fabric of how energy and probability intertwine. If classical physics is a story of certainty, objects obeying forces with predictable outcomes, quantum tunneling is a story of possibility. It reminds us that the universe doesn't deal in absolutes. Even a solid wall has a whisper of transparency, and even a particle trapped in the strongest field has a chance, however slim, to escape. That slim chance is enough to make the stars burn, to let electrons flow in our devices, and to reveal the very atoms we're made of. Every moment, everywhere in the universe, tunneling is happening silently, invisibly, effortlessly. It's the universe's quiet way of saying that the impossible isn't really impossible, just improbable. And in the quantum world, improbable things happen all the time. In the quantum world, everything is built on waves, not waves of water or sound, but waves of probability. And like all waves, they can interfere, combine, or cancel out depending on their relative phases. When those phases are perfectly aligned across a system, we say it's coherent. Coherence is what allows quantum systems to behave in ways that defy classical logic, producing interference patterns, entanglement, and all the strange effects that make quantum mechanics what it is. But coherence is fragile. The slightest disturbance, the whisper of an interaction with the environment, can make those delicate phases drift out of sync, leading to decoherence. This quiet process is the reason the quantum world looks so different from the everyday one we live in. Coherence can be thought of as the rhythm that keeps a quantum system in harmony. When particles or waves are coherent, their phases, essentially the timing of their oscillations, are locked together. This synchronization allows them to interfere predictably, creating the distinctive fringes and patterns seen in double-slit experiments. Two beams of coherent light, such as those from a laser, can overlap to form stable interference patterns, because every photon in the beam shares the same frequency and phase. If those phases begin to wander randomly, the pattern fades. The same principle applies to electrons, atoms, or any quantum system. Coherence is the invisible thread that holds the pattern of possibilities together. To see how coherence works, imagine a simple double-slit experiment again. A single electron passes through two slits, and because its wave function is coherent across both paths, it interferes with itself on the far side, forming a beautiful ripple of bright and dark stripes. But if something disturbs that coherence, say, a stray photon bouncing off the electron, the interference disappears. The electron's phase relationship between the two paths has been scrambled by the interaction. The world suddenly looks classical again. Two slits, two bright spots, no pattern. Nothing magical happened to the electron itself. What vanished was its phase memory, its ability to behave as one unified wave across multiple possibilities. This loss of coherence, decoherence, isn't destruction in the ordinary sense. It's more like information leakage. Every quantum system exists in superposition until it becomes entangled with its environment, spreading its delicate quantum information into countless surrounding particles. Once that information is dispersed, it's practically impossible to recover, and the system appears to have collapsed into a single outcome. Decoherence is not a mysterious collapse caused by observation. It's the natural process of a quantum system interacting with the messy, noisy world around it. At the microscopic level, coherence can survive remarkably long. Photons in a laser maintain coherence over kilometers, and atoms cooled to near absolute zero can behave like one giant quantum wave, perfectly synchronized in phase. In fact, the phenomenon known as a Bose-Einstein condensate is an extreme example of coherence. Thousands, or even millions of atoms occupying the same quantum state, vibrating together as one. But at larger scales, where air molecules, heat and electromagnetic noise are everywhere, coherence evaporates almost instantly. That's why we don't see interference patterns from baseballs or cars. Their interactions with the environment are so constant and overwhelming that quantum coherence disappears in a fraction of a trillionth of a second. This transition from coherence to decoherence explains why the macroscopic world feels classical, even though it's built from quantum parts. It's not that large objects stop being quantum, it's that their coherence is destroyed too quickly to notice. Every collision with a stray photon, every jostle from thermal motion, every vibration of atoms in the air robs them of their unified quantum rhythm. The boundaries of the quantum and classical worlds aren't marked by size or scale, but by isolation. The more you can shield a system from environmental noise, the longer it remains coherent, and the longer it behaves quantum mechanically. In modern technology, coherence has become both a challenge and a treasure. Quantum computers, for instance, rely entirely on maintaining coherence across qubits, the quantum bits that store information. Each qubit can exist in a superposition of 0 and 1, but only as long as coherence persists. When decoherence sets in, the qubit loses its superposition and becomes an ordinary bit, collapsing the computation prematurely. Engineers spend enormous effort cooling quantum processors to near absolute zero, isolating them from vibrations and electromagnetic fields, and correcting tiny errors, all to keep those fragile quantum phases intact for a little longer. The longer the coherence time, the more powerful the computer. Coherence is also the foundation of quantum communication. In quantum teleportation and quantum cryptography, entangled particles maintain coherent correlations across vast distances. Any disturbance, any hint of decoherence, breaks those correlations instantly, alerting users to interference or eavesdropping. This property is what makes quantum encryption theoretically unbreakable. In the strange arithmetic of quantum mechanics, coherence isn't just a curiosity, it's a resource, something that can be created, consumed, and protected like energy. Even outside the lab, coherence shapes the world we experience. Lasers, which are now so common we hardly think about them, work only because light waves inside them are coherent. The atoms in the laser cavity emit photons in perfect synchrony, amplifying one another instead of cancelling out. This is why laser light doesn't scatter or spread like a flashlight beam. It's a regimented army of photons marching in lockstep. In medicine, lasers are used for delicate surgeries. In communication, they carry information across fiber optic cables. In science, they cool atoms, trap ions, and measure distances with unimaginable precision. None of that would be possible without coherence. Decoherence, by contrast, is the quiet saboteur that keeps the quantum world from running wild. It explains why we don't see Schrödinger's cat both alive and dead, why we never find planets in superpositions of orbits, and why the universe appears stable and classical on human scales. But even here, decoherence doesn't destroy quantum mechanics, it merely hides it. Every macroscopic event, every flicker of a flame or ripple of air, is still governed by quantum laws. It's just that coherence doesn't last long enough for us to notice the interference. Understanding decoherence has also given physicists a more grounded interpretation of measurement. Rather than invoking mysterious collapses, decoherence shows how quantum probabilities become classical facts through interaction. It bridges the gap between the quantum realm and our everyday experience, offering a seamless transition rather than a sharp divide. The world doesn't stop being quantum, it just becomes too entangled with itself for the strangeness to stand out. Some researchers now explore ways to control or even reverse decoherence. By creating systems where the environment is carefully managed or even engineered, scientists can make coherence last longer than nature intended. Superconducting circuits, trapped ions, and neutral atoms cooled to microkelvin temperatures are all candidates for long-lived coherence. These are the systems behind quantum computers, atomic clocks, and precision sensors capable of measuring gravitational waves or shifts in Earth's crust at the atomic scale. In every case, the goal is the same: to preserve coherence against the constant roar of the universe. In a poetic sense, coherence is the universe at its most harmonious, a state where everything vibrates in perfect accord, where probability waves align and sing as one. Decoherence is the return to noise, to individuality, to the familiar chaos of daily life, yet both are necessary. Without coherence, quantum phenomena could never emerge. Without decoherence, the world would remain a blur of probabilities, never settling into the stable patterns we call reality. So the next time you see a laser pointer tracing a steady red dot across a wall, remember, you're looking at coherence made visible, and every flickering shadow, every sound, every sensation around you is decoherence at work, the graceful unwinding of quantum order into classical calm. Between the two lies the rhythm of the universe itself, a dance of waves and noise, harmony and loss, all playing out beneath the surface of what we call reality. When things get cold, really cold, colder than anything found naturally on Earth, the quantum world begins to take over. At those extremes, matter stops behaving like ordinary stuff and starts revealing its wave-like nature. Atoms lose their individuality and begin to act as one unified entity, forming strange, beautiful states of matter that obey the deepest rules of quantum mechanics. Two of the most striking examples are the Bose-Einstein condensate and the Fermi sea, opposites in personality, yet both products of quantum laws written in nature's smallest handwriting. To understand the Bose-Einstein condensate, imagine cooling a cloud of bosonic atoms, atoms whose total spin is an integer, closer and closer to absolute zero. Normally, atoms jostle around, each occupying its own quantum state. But as the temperature drops, their energy levels narrow, and the differences between them shrink. Eventually, at a critical temperature just a few billionths of a degree above absolute zero, the individual wave functions of the atoms begin to overlap. Instead of many separate waves, the entire collection merges into a single, giant quantum wave. The atoms lose their separate identities and behave as one. This is the Bose-Einstein condensate predicted in the 1920s by Albert Einstein and Satyendra Nath Bose, and first created in the lab in 1995. In this state, all the particles occupy the same lowest energy configuration, forming what can only be described as a single superatom, a piece of matter where every part knows what every other part is doing. If you nudge one corner of a Bose-Einstein condensate, the whole thing ripples in response like a liquid made of one synchronized thought. You can even see its quantum wave pattern under a microscope, shimmering with interference effects that normally only show up at the subatomic level. The fact that such delicate behavior can occur in a lump of atoms large enough to see with the naked eye is one of the most breathtaking triumphs of modern physics. One of the most famous examples of this phenomenon is superfluid helium. When helium-4, which is made of bosonic atoms, is cooled below about 2.1 Kelvin, it suddenly changes personality. The liquid stops resisting motion and becomes a superfluid, a substance that can flow without friction. Pour it into a container and it will climb the walls and spill over the edge, driven not by pressure or gravity but by quantum mechanics. The atoms move in perfect coordination, their individual momenta locked together in a single, coherent wave function. There's no viscosity, no turbulence, just a silent, ghostly flow that never slows down. Superfluid helium can do tricks that seem almost alive. If you spin a container of it, it doesn't rotate like an ordinary liquid. Instead, it forms an array of tiny vortices, each carrying a quantized unit of angular momentum. These vortices are direct evidence that even at the macroscopic level, quantum rules still apply. The superfluid's behavior isn't metaphorically quantum, it is quantum, made visible in a way that you can literally watch through a glass flask. While bosons love to share, fermions play by different rules. Electrons, protons, and neutrons, all fermions, refuse to occupy the same quantum state. Even at absolute zero, they can't all fall into the lowest energy level. Instead, they pile up layer by layer, each new particle forced to take a slightly higher energy until every available slot is filled. The result is what physicists call a Fermi sea, a vast collection of states filled up to a limit known as the Fermi level. This invisible sea defines much of the behavior of metals, white dwarf stars and neutron stars, where fermionic particles are packed so tightly that quantum pressure prevents collapse. In a metal, for instance, the electrons form a Fermi sea that determines how electricity flows and how the material conducts heat. At low temperatures, only the electrons near the Fermi level have enough energy to move freely, which is why metals become better conductors when cooled. Inside white dwarf stars, the same principle keeps the star from collapsing under gravity. The electrons are so densely packed that the Pauli exclusion principle, the rule forbidding them from sharing states, creates a pressure strong enough to counteract the star's own weight. This degeneracy pressure is pure quantum mechanics, powerful enough to hold up a dying star the size of Earth. But under the right conditions, fermions can find a loophole in their antisocial nature. If two fermions pair up, their spins combine to make an integer, turning them into an effective boson. This is the secret behind Cooper pairs, the bound pairs of electrons that give rise to superconductivity. In certain materials cooled to extremely low temperatures, electrons near the Fermi surface attract each other weakly through interactions with the crystal lattice. Despite their negative charges, they form pairs that move in perfect synchrony. Once paired, these electrons can occupy the same quantum state, flowing without resistance. The current in a superconductor can circle a loop indefinitely, unimpeded by heat or friction. The discovery of superconductivity in 1911 by Heike Kamerlingh-Onnes was a complete surprise, but the explanation, developed later through quantum theory, revealed the astonishing reach of Bose-Einstein behavior. What's more, similar principles apply to superfluid helium-3, a fermionic isotope of helium. When cooled far enough, helium-3 atoms pair up to act like bosons, creating a superfluid that's even more delicate and strange than its helium-4 cousin. Its flow patterns and quantum vortices are so intricate that scientists study them as analogues for black holes and early universe physics. Bose-Einstein, condensates, and Fermi seas are two sides of the same quantum coin. One shows what happens when particles share a single state, the other when they absolutely refuse to. Together they define much of the structure and stability of matter. The air you breathe, the metal in your phone, the light in your room, all behave the way they do because of the invisible bookkeeping of bosons and fermions. Perhaps the most extraordinary thing about these phases is that they bring quantum mechanics to human scales. Normally, the quantum realm hides behind the noise of temperature and motion, its subtleties drowned in randomness. But cool a system enough, strip away that noise, and quantum order emerges clear and elegant. A droplet of superfluid helium or a puff of Bose-Einstein condensate isn't just cold, it's a piece of the universe stripped down to its most fundamental rhythm. Every atom, every wave, every motion is orchestrated by the same equation, humming quietly in perfect synchrony. In laboratories around the world, physicists now trap clouds of atoms, cool them with lasers, and watch as they condense into this remarkable state of matter. The images are mesmerizing, swirls of color showing the interference patterns of a single unified quantum wave. These experiments aren't just beautiful, they open doors to studying fundamental physics in slow motion. From testing quantum gravity to simulating exotic materials, Bose-Einstein condensates have become playgrounds for exploring the limits of the possible. And yet there's something profoundly poetic about it. When matter is cooled to the point where all chaos disappears, what remains isn't silence but harmony, a perfect quantum chord. In one corner of the universe, bosons gather and sing the same note. In another, fermions stand shoulder to shoulder, filling every place they can without overlap. Together they form the structure of everything, from the hearts of stars to the tinier circuits of our machines. The deeper we look into these strange quantum seas, the more we find that the universe's most extreme states are also its most ordered. Beneath all noise and motion, matter is capable of perfect coordination. It's as if, in the coldest and most remote corners of physics, the universe finally reveals its calmest, most graceful self. A quiet reminder that order, no matter how small or fleeting, is always waiting beneath the surface. There's something magical about a material that can conduct electricity forever, without losing a single bit of energy. No sparks, no heat, no resistance, just a perfect silent flow. That's the promise of superconductivity, one of the most striking and mysterious consequences of quantum physics made visible on a human scale. When certain materials are cooled below a critical temperature, their electrical resistance suddenly drops to zero. Not almost zero, not so small it's hard to measure, but exactly zero. In that frozen quantum perfect state, electrons stop behaving like individual particles and start moving as a single unified wave. The story begins in 1911 when Dutch physicist Heike Kamerlingh Onnes, fresh off his success in liquefying helium, decided to test how metals behaved at very low temperatures. He cooled a sample of mercury down to around 4.2 Kelvin, and something astonishing happened. The resistance, which had been steadily dropping as the metal cooled, suddenly vanished. The current could now flow endlessly without losing energy. If you started it moving, it would in principle circulate forever. A century later, that simple observation remains one of the most beautiful demonstrations of quantum order made macroscopic. At first, nobody understood how such a thing could be possible. In a normal metal, electrons constantly bump into the vibrating atoms of the lattice, losing energy as heat. But in a superconductor, those collisions somehow stop. The breakthrough came in 1957, when John Bardeen, Leon Cooper, and Robert Schrieffer developed what became known as BCS theory. They realized that under the right conditions, electrons can form pairs, now called Cooper pairs, that behave not like separate fermions but like bosons. These pairs can all fall into the same quantum state, forming a single, coherent wave function that extends across the entire material. Because the pairs move in perfect synchrony, they glide through the atomic lattice without scattering. Resistance disappears, not because electrons stop moving, but because they move together in a way that no random vibration can disrupt. This collective behavior has some remarkable consequences. One of them is the Meissner effect, discovered in 1933. When a material becomes superconducting, it doesn't just allow current to flow freely, it actively expels magnetic fields from its interior. Place a magnet near a superconducting surface, and it will levitate, held up by the repulsion of its own magnetic field excluded from the superconductor's body. This isn't mere magnetic pushback, it's a direct result of the superconductor's quantum state reorganizing itself to cancel any internal magnetic flux. It's as if the material insists on remaining perfectly quiet, rejecting any outside disturbance that tries to intrude. The Meissner effect is more than a curiosity. It's a clear sign that superconductivity is a true phase of matter, like ice or steam, with its own distinct properties. It shows that superconductors aren't just perfect conductors, they're quantum systems maintaining macroscopic coherence. The same physics that governs an atom's electrons now applies to trillions of them at once, locked in step across distances visible to the naked eye. Superconductivity also led to one of the most astonishing quantum effects ever discovered, the Josephson effect. In 1962, British physicist Brian Josephson predicted that if two superconductors were separated by a very thin insulating barrier, just a few atoms thick, pairs of electrons could tunnel through that barrier without any applied voltage. This was quantum tunneling on a grand scale, electrons moving effortlessly through a wall that should have been impenetrable. Even more remarkably, if a small voltage were applied, the current would oscillate at a frequency precisely determined by that voltage, connecting electricity to time through one of the most exact relationships in physics. When Josephson's prediction was confirmed experimentally, it opened an entire new world of technology. A Josephson junction, the sandwich of two superconductors with a thin insulator between, became the cornerstone of ultra-sensitive devices known as squids, or superconducting quantum interference devices. A squid exploits the fact that superconducting currents are governed by a quantum phase that can interfere with itself, much like light waves in a double-slit experiment. When magnetic flux passes through a superconducting loop containing Josephson junctions, it shifts the phase of the current ever so slightly. By measuring those shifts, a squid can detect magnetic fields as faint as 1 part in a trillion of Earth's own magnetic field. They're sensitive enough to measure the brain's magnetic activity, detect flaws in materials, or even pick up the magnetic signature of a single nerve firing. The precision of the Josephson effect goes beyond measurement. Because the frequency of the oscillating current depends only on fundamental constants, the charge of the electron and Planck's constant, it serves as a natural voltage standard. National laboratories around the world use Josephson junctions to define the volt with astonishing accuracy, linking electrical units directly to the bedrock of quantum mechanics. Superconductivity also provides a glimpse into how deeply quantum mechanics can shape macroscopic matter. The current flowing through a superconducting loop isn't a random swarm of electrons, it's a single quantum wave wrapping around itself. This means it can interfere, oscillate, and even exist in superpositions, just like a photon or an atom. In the past 2 decades, scientists have learned to harness these properties to build one of the most promising architectures for quantum computing. In a superconducting quantum computer, tiny circuits made of Josephson junctions act as qubits, the quantum analogues of bits. Each qubit can represent both 0 and 1 simultaneously, encoded in the direction of a current circulating around a loop. Because these circuits are macroscopic, visible under a microscope, they allow engineers to build quantum systems large enough to manipulate directly. Yet, because they are superconducting, they behave as pure quantum objects capable of entanglement, superposition, and interference. By coupling many such qubits together, researchers can perform calculations that, in principle, no classical computer could match. The challenge, of course, is coherence. Superconductors are remarkably robust against some kinds of noise, but even the tiniest interaction with the outside world can disturb their delicate quantum states. That's why these circuits are cooled to temperatures just a few thousandths of a degree above absolute zero, housed in elaborate refrigerators that resemble gleaming silver chandeliers. Inside those frigid chambers, electrons pair up and glide through their crystalline playgrounds in unison, their quantum choreography unfolding in perfect silence. Beyond computing, superconductivity has already transformed technology in countless ways. MRI machines use powerful superconducting magnets to peer inside the human body. Particle accelerators rely on them to steer and focus beams at near-light speed. Maglev trains float effortlessly above their tracks, supported by superconducting magnets repelling the rails below. In all these cases, the effect that began as a laboratory curiosity in 1911 has become an indispensable tool of modern science and engineering. And yet, despite a century of progress, superconductivity still holds mysteries. Researchers continue to hunt for materials that can become superconducting at higher temperatures, ideally room temperature. In recent years, compounds of hydrogen and rare metals have shown tantalizing results, becoming superconducting under immense pressures. If the phenomenon could ever be achieved in everyday conditions, the impact would be revolutionary. Lossless power grids, perfectly efficient motors, and electronics without waste heat. At its core, superconductivity is a story about cooperation. It's what happens when countless electrons, which normally repel one another, fall into alignment and act as one. It's nature showing that when individual particles give up their independence and move together in perfect phase, resistance vanishes. The Josephson effect and its offspring, squids, qubits, and superconducting magnets, are all echoes of that harmony, applications born from a single idea: that even in the coldest, most silent conditions, the universe is still humming with coordination. So while most of us think of electricity as something that flows with friction, wasting energy as it goes, superconductivity reminds us that there's another way, one that's perfectly ordered, perfectly quiet, and perfectly efficient. It's quantum mechanics not as chaos, but as calm. The same laws that make the microscopic world unpredictable can, under the right conditions, produce a state of absolute precision. In that stillness where resistance disappears and waves move as one, we glimpse a rare kind of perfection, the universe, finally, without loss. Quantum mechanics may sound like something that only belongs in research labs or thought experiments, but it quietly powers the modern world. Every screen, every smartphone, every computer chip is built on the invisible framework of quantum physics. It's in the light from LEDs, the timing of GPS signals, the hum of MRI machines, and even the electricity flowing through transistors. These strange rules that govern atoms and waves aren't just curiosities, they're the reason technology works at all. Start with the transistor, the tiny switch that changed human history. A single computer chip can contain billions of them, each one turning currents on and off faster than any mechanical part could ever move. Transistors work because of quantum mechanics. Inside a semiconductor, electrons don't roam freely like in a metal, nor are they locked in place like in an insulator. Instead, they occupy specific energy bands allowed by quantum rules. Between these bands is a forbidden region called the band gap, where electrons can't exist. By adding impurities, engineers can tweak how easily electrons jump across that gap, creating materials that behave like one-way streets for current. The result is a world where electrons can be guided, amplified, and controlled with breathtaking precision. The logic gates inside your phone and computer are nothing more than quantum tunnels carefully shaped by human design. The rules that make quantum mechanics seem weird, discrete energy levels tunneling probability, are the same rules that make digital technology possible. Without them, there would be no laptops, no satellites, no modern civilization. From transistors, it's a short step to light itself. Quantum physics explains how light and matter exchange energy one photon at a time. This is the principle behind LEDs, light-emitting diodes, which are now so common that we rarely pause to consider how extraordinary they are. In an LED, electrons are injected into a semiconductor where they fall from a higher energy band to a lower one, releasing the difference as a photon. The colour of the light depends on the size of the band gap. A small gap gives red, a larger one blue. This process is elegantly efficient because every photon is born from a single quantum jump, not from heat or waste. The same idea powers lasers, perhaps the most famous quantum devices of all. A laser, short for light amplification by stimulated emission of radiation, relies on coaxing electrons into excited states, then encouraging them to fall back in unison, releasing identical photons. Those photons stimulate others to do the same, creating a cascade of perfectly synchronized light waves. The result is coherence, light that marches in lockstep, each wave crest aligned with the next. Because of this precision, lasers can cut through steel, carry data through fiber optic cables, scan barcodes, and even perform delicate eye surgery. Every smooth red beam you see at a checkout counter or concert is a perfectly tuned quantum chorus, singing one note in unison. Solar cells too are built on the same principle but in reverse. Instead of turning electrical energy into light, they turn light into electricity. When a photon strikes the surface of a solar panel, its energy can lift an electron across the band gap in a semiconductor, creating a free charge that flows as current. This is the photovoltaic effect, a process Albert Einstein first explained in 1905, earning his Nobel Prize. Each tiny cell on a solar panel is like a miniature photon trap, converting sunlight into electrons that travel down wires to power homes, satellites, and spacecraft. The world's most promising source of renewable energy depends on the quantum dance between light and matter. If quantum physics governs how we make energy and light, it also governs how we measure time. The ticking of an ordinary clock depends on mechanical motion, gears, springs, pendulums, but the ticking of an atomic clock depends on the oscillations of atoms themselves. In the mid-20th century, scientists learned how to use microwave radiation to probe transitions between the energy levels of cesium atoms. These transitions occur with astonishing regularity, 9,192,631,770 cycles per second to be exact. That number defines the second. Modern atomic clocks are so stable they lose or gain less than a second over the entire age of the universe. GPS systems rely on them to synchronize satellites and calculate precise positions. A timing error of just a few nanoseconds could throw off a location by several meters, so the global navigation systems guiding planes, ships and phones all depend on quantum precision. Even the stock market's high-frequency trading algorithms rely on atomic time. Every now in our world, every timestamp, every digital heartbeat, is kept in tune by the quiet rhythm of electrons jumping between quantized energy states. Another remarkable application of quantum physics is found inside hospitals, the MRI scanner. MRI, short for magnetic resonance imaging, works by probing the quantum property of spin in atomic nuclei, particularly those of hydrogen in the body's water molecules. When placed in a strong magnetic field, these spins align like tiny compass needles. A pulse of radio waves nudges them out of alignment, and as they relax back, they emit faint signals. By detecting those signals and mapping how they vary across tissues, the machine builds detailed images of the body's interior without a single incision. The clarity of those scans, down to millimeters or even less, comes directly from the predictable quantum behavior of nuclear spins in magnetic fields. It's a way of listening to the body's atoms hum their quiet tune. Each of these technologies, transistors, LEDs, lasers, solar cells, atomic clocks, MRI, illustrates the same profound truth. Quantum mechanics isn't confined to laboratories or thought experiments. It's woven into the fabric of everyday life. The lights in your room, the internet carrying this very sentence, the navigation system guiding you home, all depend on electrons leaping between quantized levels and photons following the probabilistic rules first glimpsed more than a century ago. Even seemingly mundane materials owe their properties to quantum mechanics. The color of metals, the transparency of glass, the hardness of diamonds, all come from the arrangement of electrons in quantized energy bands. The resistance of copper wires, the behavior of magnets, the properties of superconductors, each emerges from the collective behavior of countless particles obeying the same microscopic laws. Every device around you is, in its own quiet way, a quantum system scaled up and domesticated. And yet, for all its complexity, quantum technology also has a strange elegance. Once you understand how particles share energy and information, the chaos of the world begins to look ordered. A transistor switching in a microchip, a laser emitting coherent light, an atom vibrating in a clock. They all follow the same mathematics. The universe, at its smallest scales, plays by simple, beautiful rules, and we've learned just enough to borrow them. Looking ahead, the boundary between quantum technology and everyday technology is fading fast. Quantum computers are beginning to perform specialized tasks. Quantum sensors are being developed to detect gravitational waves and underground minerals. Quantum networks may someday enable unhackable communication, but in truth, the quantum revolution has already happened. It began when engineers first learned to shape the energy bands of silicon and capture the light of a single photon. The world around you hums quietly with quantum precision. Every glowing pixel, every electronic pulse, every perfectly timed signal is part of a vast invisible orchestra. Electrons, photons, and atoms performing their subtle symphony beneath the surface of ordinary life. And that's perhaps the most astonishing part of all. the most exotic physics in the universe isn't hidden in distant galaxies or particle colliders. It's right here, humming in your pocket, lighting your room, guiding your way home, reminding you every second that you live in a world built on the smallest possible miracles. Computers as we know them today are built on a simple idea. Everything can be broken down into bits. Each bit can be either 0 or 1, off or on, true or false. This binary logic, when combined and scaled, can represent anything, from an image to a song to the orbit of a spacecraft. But quantum physics offers a twist to that logic, one that could transform computation itself. In the quantum world, a bit doesn't have to choose between 0 and 1. It can hold both at once, hovering between possibilities until measured. This strange state is called superposition, and it's the foundation of the qubit, the quantum bit. A qubit can exist as a mixture of 0 and 1 simultaneously, represented not by a switch, but by a point on the surface of what physicists call the Bloch sphere. Imagine a globe where the North Pole represents 0, the South Pole represents 1, and every point in between represents some blend of the two. The state of a qubit isn't fixed, it's a wave of probability that can interfere with itself, amplifying or cancelling out different outcomes depending on how it's manipulated. This flexibility gives qubits their unique power. Instead of testing one possibility at a time, they can explore many in parallel. In classical computing, if you have 2 bits, they can represent 4 possible combinations: 0, 0, 0, 1, 1, 0, and 1, 1, but only one at a time. 2 qubits, by contrast, can represent all 4 combinations simultaneously. 10 qubits can represent over 1,000 possibilities at once. 20 qubits can hold over 1,000,000. And 50 qubits. That's more combinations than there are atoms in the human body. This exponential scaling is what makes quantum computing so tantalizing. It grows in power far faster than classical machines ever could. But superposition alone isn't enough. The real magic happens when qubits become entangled. Entanglement links qubits so that the state of one instantly influences the other, no matter how far apart they are. When 2 qubits are entangled, measuring one tells you something about the other, even before you check it. In a quantum computer, this allows information to be spread across the entire system in ways that classical bits can't replicate. Entangling operations, known as quantum gates, create intricate webs of correlation, letting the computer process multiple layers of information at once. Entanglement isn't just a neat trick, it's the glue that makes quantum algorithms work. When qubits are entangled, the system as a whole becomes more than the sum of its parts. This interconnectedness allows quantum computers to manipulate probability itself, sculpting the outcomes through interference. In essence, the computer sets up a series of quantum waves representing all possible answers to a problem, then cleverly arranges the computation so that the wrong answers interfere destructively, while the right ones reinforce each other. When the system is finally measured, the quantum haze collapses, not into chaos, but into the most likely correct solution. This is how quantum algorithms differ from classical ones. A classical algorithm walks step by step, like a detective following a trail. A quantum algorithm lets all possible paths be explored at once, then interferes them to highlight the path that leads to the right conclusion. It's a kind of computational parallelism that doesn't just make things faster, it changes the rules of what's possible to compute. For example, Shor's algorithm can factor large numbers exponentially faster than any known classical method, threatening to upend modern encryption. Grover's algorithm can search through unstructured data far more efficiently. And newer quantum algorithms promise breakthroughs in chemistry, optimization, and even the simulation of quantum systems themselves. But the quantum world is fragile. Superposition and entanglement don't last long before decoherence, the loss of quantum order, sets in. The smallest disturbance from the environment, a stray vibration or flicker of heat, can collapse the delicate quantum state and destroy the information. That's where quantum error correction comes in, one of the most ingenious ideas in modern science. In classical computing, error correction is straightforward. Copy the data, compare the copies, and fix discrepancies. But in quantum computing, the no-cloning theorem forbids making exact duplicates of unknown quantum states. Instead, physicists found a way to encode one logical qubit into many physical qubits, distributing the information in such a way that small errors can be detected and corrected without disturbing the computation. It's like hiding a secret inside an orchestra. Even if one musician plays the wrong note, the melody can still be reconstructed from the others. Quantum error correction is what makes large-scale quantum computing possible in theory. Without it, qubits would lose coherence too quickly to perform meaningful work. With it, quantum computers could one day run for hours or even days, solving problems that are utterly intractable for classical machines. The current frontier of research isn't just about making more qubits, it's about making better qubits, with longer coherence times, higher fidelity, and better protection from noise. Different technologies have emerged in this race. Superconducting qubits, made from Josephson junctions, are among the leading contenders, used by companies like IBM and Google. They operate at temperatures just a few thousandths of a degree above absolute zero, where electrons flow without resistance. Trapped ion qubits, on the other hand, use individual atoms suspended in the electromagnetic fields, manipulated by laser pulses. They're incredibly stable and precise, though slower to operate. Other approaches, like photonic qubits made of light, or topological qubits designed to be inherently fault-tolerant, represent the cutting edge of quantum engineering. What's striking is how closely quantum computing mirrors the principles of nature itself. The universe doesn't compute outcomes by testing them one at a time. It allows all possibilities to coexist, then interferes them through the laws of physics to produce reality as we experience it. Quantum computers, in their own way, are designed to harness that same natural efficiency. They don't replace classical computers, they complement them, opening doors to problems where the classical approach simply runs out of time. Even in its infancy, quantum computing has already proven its potential. In 2019, a quantum processor built by Google performed a specific calculation in about 200 seconds that would have taken a supercomputer thousands of years. While that particular task was chosen for demonstration rather than utility, it proved the principle. Quantum devices can reach realms of computation that classical ones cannot touch. Since then, the field has only accelerated, with researchers increasing qubit counts, reducing errors, and exploring new architectures that inch closer to practical quantum advantage. But beyond the technology, there's something deeply poetic about the idea. A qubit, suspended between 0 and 1, embodies uncertainty, not as a flaw, but as power. Where classical computing relies on certainty, quantum computing thrives on possibility. It uses the fuzziness of the quantum world not as a limitation, but as a tool. Every calculation is a negotiation between what could happen and what must, a symphony of probabilities orchestrated into precision. If the 20th century was defined by mastering the electron, the 21st may be defined by mastering its uncertainty. Quantum computers are still fragile, expensive, and experimental, but their promise is immense. The ability to simulate chemistry at the molecular level, optimize complex networks, and perhaps even uncover new laws of nature. In every sense, they are humanity's attempt to think as the universe thinks. Parallel, probabilistic, and profoundly interconnected. One day, when quantum computers become as commonplace as laptops, we may look back on the qubit the way we now look at the transistor, the simplest possible object that changed everything. But for now, it remains something extraordinary, a single silent unit of possibility, holding 0 and 1 together in the same breath, waiting to decide what reality will be. Quantum mechanics may appear limitless, a world where particles can be in two places at once, and information can stretch across galaxies. But even this realm of strange freedom comes with boundaries, precise, elegant limits that define what can and cannot be done. These rules aren't restrictions in the human sense. They're the built-in guardrails of nature's logic, ensuring that the universe remains consistent even when it's unpredictable. Some of these principles, like the no-cloning theorem, complementarity, and the inevitability of measurement disturbance, reveal the deep philosophical beauty of the quantum world. Knowledge always comes at a cost, and context always matters. One of the clearest expressions of that is the no-cloning theorem, which says you cannot make an exact copy of an unknown quantum state. In the classical world, copying is easy. You can duplicate a file, a photograph, or even a strand of DNA. But quantum information resists duplication because it's not just a set of values, it's a delicate superposition of possibilities. To clone a quantum state, you'd have to know precisely what it is, but measuring it changes it. The very act of trying to make a copy destroys the original information. It's a rule woven into the mathematics of the universe, not a technological limitation. This restriction has profound implications. It means you can't eavesdrop on quantum communication without leaving a trace, which is why quantum cryptography can, in principle, be perfectly secure. Any attempt to copy the state of a photon traveling down a quantum communication channel inevitably disturbs it, alerting the sender and receiver that someone has peaked. The no-cloning theorem is less a rule about technology and more a statement about reality itself. There's a built-in privacy to nature. Information is not something that can be infinitely duplicated like a paragraph of text. It's something that exists only in context, unique to each system and its history. The impossibility of cloning connects to another deep truth about the quantum world. Measurement is never neutral. In classical physics, you can observe something without changing it. You can measure the temperature of a pot of water or the position of a planet without altering their behavior in any meaningful way. In quantum mechanics, however, measurement is participatory. When you measure one property, you inevitably disturb others. This isn't clumsiness or technological imperfection. It's built into the logic of quantum states. For example, you can measure the position of an electron very precisely, but doing so disturbs its momentum. Conversely, if you measure its momentum, its position becomes uncertain. This is the essence of Werner Heisenberg's uncertainty principle. But it's more than just a limit of precision. It's a reflection of how information in the quantum world is structured. Certain properties simply don't coexist in a definite form. When you measure one, You force the system to choose a reality for that property, and in doing so erase information about its complementary aspect. Nature seems to say, you can ask me this question or that one, but not both at once. This idea that measurement changes the system leads directly into another cornerstone of quantum logic, contextuality. In the classical world, the properties of an object exist independently of how you measure them. A coin has two sides, whether you flip it or not. But in the quantum world, outcomes depend on the set of measurements being made, the context of the observation. In other words, the result of measuring one property can depend on which other properties are being measured alongside it, even if those properties don't seem directly related. This means quantum systems don't carry fixed, hidden values for all measurable quantities. Instead, the act of measurement helps define what those values are. It's not that particles are sneaky or incomplete. It's that reality, at the quantum level, is fundamentally relational. What you see depends on how you look. The Cauchy-Specker theorem formalizes this, proving mathematically that no model can assign definite outcomes to all possible measurements without contradicting the predictions of quantum mechanics. In a deep sense, the universe doesn't contain pre-written answers. It writes them when asked. All of these ideas, no cloning, measurement disturbance, contextuality, flow from a broader principle first articulated by Niels Bohr, complementarity. Bohr proposed that certain properties of quantum systems, though seemingly contradictory, are both necessary to describe reality. Light, for instance, is both a wave and a particle, but you can never observe both aspects at once. The experiment you perform determines which side of its nature is revealed. The particle and wave pictures aren't rival explanations. They're complementary views of a deeper truth. Complementarity isn't confined to light. It pervades the entire quantum world. Position and momentum, energy and time spin along different axes, all come in complementary pairs. The more clearly you see one, the more the other fades into uncertainty. This interplay isn't a flaw in our instruments or understanding. It's a fundamental feature of how the universe balances information. Every gain in knowledge about one aspect of a system requires a sacrifice of knowledge about another. These theorems and principles remind us that reality isn't a static collection of things waiting to be catalogued. It's a network of relationships, where what can be known depends on how you choose to know it. The quantum world doesn't allow us to take snapshots of absolute truth. It only lets us glimpse one perspective at a time, and each perspective changes the landscape just by being chosen. Even in the growing field of quantum technology, these limits remain guiding stars. The no-cloning theorem underpins the security of quantum communication. Complementarity and contextuality shape the design of quantum computers, where interference patterns encode computation through controlled measurement. The unavoidable disturbance caused by observation is what allows quantum sensors to detect infinitesimally small changes. They trade certainty for sensitivity. Far from being inconveniences, these constraints are what make quantum devices both possible and reliable. At a deeper level, these limits are philosophical reminders about the nature of knowledge. In classical thinking, the universe is like a library, with every fact waiting patiently to be discovered. In the quantum view, it's more like a conversation. The questions we ask shape the answers we get. There's no such thing as observing without participating, and no such thing as copying without changing. Even information itself, that most abstract of entities, obeys physical laws. It can't be cloned, destroyed, or detached from the system that holds it. It's easy to think of limits as boundaries, But in quantum mechanics, they're more like invitations. They tell us not just what can't be done, but what new possibilities arise when we work within them. You can't clone a quantum state, but you can teleport it through entanglement. You can't measure everything at once, but you can choose what to know with exquisite precision. You can't describe reality from outside it, but you can become part of its unfolding story. These theorems aren't barriers, they're the architecture of the possible. They're the fine print in the laws of the universe, ensuring that even in a world ruled by chance, coherence and consistency endure. And as strange as they seem, they make the universe not less knowable, but more elegant. They remind us that certainty has a cost, knowledge has context, and that every measurement, from the smallest particle to the largest telescope, is not just a glimpse of reality, but a handshake with it. Imagine a world where messages can't be hacked, secrets can't be copied, and even the act of eavesdropping leaves a visible scar. That's the promise of quantum communication, a field that takes the strangeness of quantum mechanics and turns it into the most secure way of sharing information ever conceived. It works not by hiding data behind complex encryption algorithms, but by using the laws of physics themselves to guarantee privacy. In this realm, security doesn't depend on clever coding. It depends on nature's refusal to let you peek without leaving fingerprints. One of the simplest yet most powerful tools in this new world is quantum key distribution, or QKD. In ordinary cryptography, two parties share a secret key, a string of random bits used to encrypt and decrypt messages. But distributing that key safely is always the weak link. In QKD, the key is encoded into quantum states, often using photons with different polarizations. Because of the way measurement works in quantum mechanics, any attempt to intercept or copy those photons inevitably disturbs them, changing their properties. The sender and receiver can then compare a portion of their data to check for signs of tampering. If the error rate is higher than what random noise would produce, they know someone has been listening. This system doesn't rely on mathematical difficulty, as classical encryption does. It relies on physical law. No matter how powerful a computer an eavesdropper has, even one that's itself quantum, they can't break the security without detection. In a sense, QKD turns the uncertainty principle into a bodyguard. The more you try to know, the more you reveal that you're looking. Over the last few decades, quantum key distribution has moved from theory to reality. Cities like Beijing, Vienna, and Geneva have demonstrated quantum secure networks, sending encryption keys over tens or even hundreds of kilometers of optical fiber. In 2017, China's Micius satellite beamed entangled photons between ground stations thousands of kilometers apart, creating a secure quantum link through space. These experiments mark the first steps toward what some call the quantum internet, a network that uses entanglement not just for encryption, but for communication, synchronization, and computation itself. But perhaps the most mind-bending idea in quantum communication is quantum teleportation. Despite the science fiction connotations, it doesn't involve matter disappearing and reappearing somewhere else. Instead, it's about transferring the state of a particle from one location to another without physically moving the particle itself. The process begins with a pair of entangled particles, let's call them A and B. One particle stays with the sender, the other travels to the receiver. The sender then performs a special kind of joint measurement on particle A and another system whose state they want to transmit. That measurement destroys the original state, but also creates a set of classical data. When the sender transmits that data through an ordinary communication channel, the receiver can use it to transform their particle, B, into an exact replica of the original state. In effect, the quantum information has been teleported from one place to another, its properties perfectly reconstructed, but without any physical transfer of particles. No cloning occurs, and no faster-than-light signaling happens. Both quantum entanglement and classical communication are needed. It's a process that sounds like magic, but has been demonstrated countless times, from tabletop setups to satellite experiments. The implications are enormous. Teleportation could one day allow distributed quantum computers to share states instantaneously, or enable secure quantum networks where information moves without ever existing in a vulnerable form. At the heart of both quantum cryptography and teleportation lies something deceptively simple: randomness. True randomness is surprisingly hard to achieve. Classical random number generators, whether in software or hardware, always rely on algorithms or physical processes that are only pseudo-random. They can be predicted if you know enough about the system. Quantum physics, however, offers randomness that's fundamentally unpredictable. When a photon passes through a polarizing beam splitter, it has a 50-50 chance of being transmitted or reflected, and no hidden variable determines the outcome. The result isn't just random in practice, it's random in principle. Quantum random number generators are now commercially available, used in encryption, gaming, and scientific simulations. They produce sequences of bits that no adversary, no matter how clever, could ever foresee. Every coin flip in a quantum system is pure chance, an unrepeatable event born from the very indeterminacy that defines the universe. It's poetic, really. The same uncertainty that once puzzled Einstein now guarantees the integrity of digital security. But as powerful as quantum communication is, it faces one stubborn challenge: distance. Entanglement and quantum states are fragile, easily disrupted by noise and loss as they travel through fiber or air. Classical signals can be amplified as they weaken, but quantum signals cannot be cloned or copied without destroying their information. This makes long-distance communication tricky. Enter the quantum repeater, a device designed to extend entanglement step by step, linking distant nodes into a single coherent network. A quantum repeater works by creating entangled pairs across short segments of a network, then performing operations called entanglement swapping to connect those segments together. Each node stores entangled particles briefly in quantum memory while synchronizing with others, effectively relaying entanglement without ever measuring or amplifying it directly. The process is slow and technically demanding, but it's the key to scaling quantum communication beyond city limits and into global networks. Researchers envision a future where quantum repeaters, satellites, and ground stations form a worldwide lattice of entanglement, a backbone for secure communication, distributed quantum computing, and ultra-precise timekeeping. The beauty of quantum communication is that it takes what once seemed like weaknesses, the fragility of quantum states, the unpredictability of measurement, and turns them into strengths. You can't copy quantum information, so your data can't be stolen undetected. You can't predict a measurement outcome, so your random numbers are truly random. You can't amplify entanglement without disturbing it, so you build networks that respect the laws of nature instead of fighting them. Every constraint becomes a feature, every limitation a safeguard. Beyond security, quantum communication also forces us to rethink what information really is. In classical physics, information is something we can store, copy, and move freely. In the quantum view, information is inseparable from the system that carries it. It's a physical quantity, as real as mass or energy. When you communicate using quantum states, you're not just sending messages across space, you're extending correlations between two distant parts of the universe. You're literally weaving space together with shared probability. What's remarkable is how seamlessly this all fits into everyday life. Quantum secure communication systems are already being tested for banking, defense, and satellite networks. Quantum random number generators are finding their way into smartphones and cybersecurity chips. Even if most people never see or think about the quantum mechanics behind it, these technologies are quietly reshaping the foundation of digital trust. In a way, quantum communication is the modern world's quiet return to simplicity. Instead of building higher mathematical walls to keep secrets safe, we've turned to the universe itself and asked it to enforce the rules. And the universe has obliged, with uncertainty, entanglement, and the unbreakable bond between observation and knowledge. If classical communication is about shouting across the void, quantum communication is about whispering in perfect synchrony, secure, invisible, and utterly unrepeatable. Every photon, every entangled pair, every flicker of uncertainty carries a message that can't be forged or overheard. And in that faint shimmer of light between sender and receiver lies one of the most extraordinary truths of all. That information, like everything else in the quantum world, doesn't just travel, it connects. For all its precision and success, quantum mechanics leaves one enormous question dangling in the air. What does it mean? The equations work flawlessly. They describe atoms, predict lasers, explain stars, and power the entire digital world. Yet no one fully agrees on what those equations are saying about reality itself. Quantum mechanics gives us a set of rules for calculating probabilities, how likely it is that something will happen when we measure it, but it doesn't tell us what the world is doing when we're not looking. To fill that gap, scientists and philosophers have offered interpretations, stories we tell ourselves to make sense of the math. Each interpretation paints a different picture of the same underlying truth, like different lenses over the same landscape. In the early days of quantum theory, the dominant view was what came to be known as the Copenhagen interpretation, shaped by Niels Bohr and Werner Heisenberg in the 1920s. According to this view, quantum mechanics doesn't describe an objective world that exists independently of observation. Instead, it describes the outcomes of measurements, the interface between observer and system. The wave function, that beautiful mathematical object that encodes all possible states of a particle, isn't a physical wave in space. It's a catalogue of possibilities. When you perform a measurement, one of those possibilities becomes real, and the wave function collapses to reflect that outcome. Bohr's version of reality was pragmatic and philosophical all at once. He argued that asking what's really happening inside an atom when you're not measuring it is meaningless. Quantum mechanics only tells you what you can say about nature, not what nature is. Many physicists embrace this modest stance because it worked. The equations predicted everything correctly, and that seemed enough. But not everyone was satisfied. Einstein, for one, couldn't accept a universe that refused to exist until it was observed. "Do you really believe the moon isn't there when you're not looking at it?" he famously asked. For those uneasy with the idea of wave function, collapse, and observer-dependent reality, other interpretations took shape. One of the most striking is the many worlds interpretation, proposed by Hugh Everett in 1957. Everett took the equations of quantum mechanics at face value and refused to add collapse as a separate rule. In his view, the wave function never collapses, it simply evolves. When a quantum measurement occurs, all possible outcomes happen simultaneously, each in its own branch of reality. The universe splits, creating parallel worlds for every quantum event. In one world, a particle lands on the left. In another, it lands on the right. In one world, Schrödinger's cat lives. In another, it doesn't. To Everett, this was not fantasy but necessity. The math already allowed for superpositions, states where something is both this and that at once. Rather than destroying that richness with collapse, he kept all the possibilities and reinterpreted measurement as entanglement between observer and system. You don't see the cat as both alive and dead because your own state becomes entangled with one outcome or the other. From your perspective, only one world remains visible, though the other persists just as real. The many worlds interpretation removes randomness entirely. The wave function evolves deterministically, governed by the same equations everywhere. What we experience as chance is merely our position within the branching multiverse. It's an elegant and audacious idea, one that eliminates the collapse problem, but replaces it with an infinity of unseen realities. Some physicists find it irresistible, others find it extravagant, like using a galaxy to explain a grain of sand. Then there's the pilot wave theory, or de Broglie-Bohm interpretation, which imagines particles always having definite positions, guided by a hidden wave. This pilot wave evolves according to Schrödinger's equation, steering particles along deterministic trajectories that look random only because we can't see the full picture. In this view, the uncertainty in quantum mechanics arises not from indeterminacy, but from ignorance. The particle knows exactly where it is, and the wave knows exactly how to guide it. The observer's role is no longer mysterious. We're simply uncovering part of a pre-existing reality. Pilot wave theory restores a sense of cause and effect that's comforting to many. It keeps the universe tidy, with clear paths and definite outcomes, while still reproducing all the predictions of standard quantum mechanics. Yet it also introduces its own strangeness. The guiding wave must be non-local, meaning it can influence particles instantaneously across vast distances. Einstein might have bristled at such spooky action, but that's precisely what experiments show the quantum world doing. The pilot wave approach doesn't make quantum mechanics less weird. It just hides the weirdness in new corners. Other interpretations take a more personal view of probability itself. Cubism, short for quantum Bayesianism, argues that the wave function isn't a description of an external reality at all, but a reflection of an observer's beliefs about possible outcomes. In this interpretation, quantum mechanics is a user's manual for making rational decisions in a world governed by uncertainty. Measurement outcomes are personal experiences, not objective facts existing independently of the observer. It's a radical shift. Instead of trying to describe what's really out there, Cubism focuses on how we, as agents within the universe, assign meaning and expectation. While Cubism may sound abstract, it carries a certain elegance. It sidesteps debates about collapse and hidden variables by treating quantum probabilities as tools for organizing personal experience. There's no cosmic wave function stretching across all of space, only information and belief, updated with every interaction. To some, this feels almost philosophical. To others, it's the most honest acknowledgement of what quantum theory truly provides. Not a map of reality, but a guide to navigating it. There are many more interpretations beyond these. Objective collapse models that add physical mechanisms for wave function collapse. Relational interpretations that see quantum states as existing only between interacting systems and even information-based views that treat the universe itself as a quantum computer. Each interpretation answers the same question differently. What does the wave function represent, and when, if ever, does it stop being a wave of probabilities and become a single reality? Yet here's the most remarkable thing. No matter which interpretation you choose, the predictions stay exactly the same. Whether you imagine countless parallel universes, hidden guiding waves, or subjective probabilities, the outcomes of every experiment agree. The photons, electrons, and atoms behave identically. The equations don't care what story you tell, they just work. In that sense, quantum mechanics is like a language we've learned to speak fluently, even if we don't entirely understand what we're saying. This unity amid disagreement is both humbling and liberating. It shows that the universe allows multiple ways of being understood, and that its truth might be deeper than any single narrative can capture. The mathematics gives us the rhythm, but the meaning, what we think those rhythms mean, is up to interpretation. Perhaps in the end that's the quiet beauty of it. Quantum mechanics doesn't hand us certainty. It offers mystery shaped by precision. Every interpretation is a mirror reflecting a different aspect of ourselves, our desire for order, our tolerance for ambiguity, our comfort with infinity. The equations are the same, the predictions unchanging, but the stories they inspire remind us that understanding isn't just about finding answers, it's about learning to live gracefully with the questions. In a universe that seems to exist in layers of possibility, maybe the truest interpretation is the simplest one, that the world, like the wave function itself, contains all its stories at once, and each of us, in observing it, brings one version gently into focus. And that brings us to the end of tonight's quiet journey through the quantum world, where certainty fades, probabilities hum, and even empty space is full of possibility. If you enjoyed drifting through these 101 quantum facts, it would really help the channel if you gave the video a like. It may seem small, but those likes tell the YouTube algorithm that this kind of calm, educational content is worth sharing, and it helps other curious minds find it too. If you're new here, please consider subscribing to The Sleepy Scientist for more relaxing explorations of science, space, and everything in between. And for those already subscribed, thank you so much for being part of this growing, peaceful community. Don't forget to tap the notification bell so you'll know when the next video is ready to drift off with. I'd also love to hear your thoughts and ideas. If there's a topic you'd like to see explored slowly and calmly in a future video, feel free to leave a suggestion in the comments. Until next time, may your thoughts settle gently, your curiosity stay bright, and your night be full of quiet wonder.